So, hello everyone. Welcome back. Logistics quiz. Gosh, which one is it now? Quiz 3 is due this week. Remember, quiz 3 is on Gauss's law. And electric potential energy has a little bit of voltage stuff in it as well. So something I also want to mention to you all, I had a lot of people come to my office hours on Tuesday, which was great. Loved it. Lots of people came. It was a great time. I had about between 8-9 people in my room, which is kind of the cap I can fit. It's like between 8 and 10 people, depending on how crazy the day. Awesome. Loved it. Got to help people. Gauss's law was pretty much the common questions. If you haven't started practicing those, make sure you do. Make sure you draw a picture, all that good stuff. What I want to mention to y'all is, one, it's great to go to someone and get additional help. That could be me, that could be the helper, that could be all those things. What I do want to point out is my Monday and my Wednesday office hours tend to have no one in them. So my Tuesday was packed, which was great. Loved it. Definitely feel free to come after class on Tuesday. But my Wednesday one, that's when we have the 2 hours, I just had 3 people in there. And so it's always advantageous to go to the ones that have less people, because then I can give you more time and more focus. Whereas when there's a lot of people, I am ping-ponging around, it's just a time is a commodity, right?
You think it's because it's just the hours aren't bringing a lot of people? Because the ones that don't work well for them.
It's because on Tuesday it's right after class, so it's definitely it's easy, it's convenient. That's the easiest one, which is why I picked it during that time. The reason I'm not able to do that for Thursday as well is I try to set them at different times throughout the week, but at the same time, if someone had a conflict on Tuesday, they're going to have the exact same conflict on Thursday. Yeah?
I'm not sure if this is the case for other people, but I have class during office hours most of the time.
Okay. Yeah, and that's one of those, unfortunately, it's almost impossible for me to pick office hours that won't have conflicts. I just try to do a variety of them to find some time that works for people. Well, so one potential idea is maybe in future, before I do office hours, I'll get people's schedules and time, whatever, but that's a whole rule. What I do want to mention to you is I'm not the only resource. So again, I love for y'all to come visit me. Please do. You will find it beneficial, not because I'm anything amazing, but because in-person tutor, one-on-one help goes a long way. If you haven't learned that yet, you will at some point. One-on-one attention helps. What I want to remind you of as well is if you are in need of assistance, there's other people than myself as well. So say my times don't work for you. This is an announcement I sent out previously, and it might be more interesting and relevant to y'all now that you're going through problems, maybe running into challenges. You got SI, you got SARC. And then remember, there's this help room that's also located in PSV, and this is filled with times and people that you can go to. You can go to anyone who has PHY 2049 after them, or anyone that's got a little asterisk next to them. Those are the people you can go to, and there is tons. Tyler, again, reminder, he's literally in my other class. He is the learning assistant in the class I teach later this day. Leo was a previous learning assistant. He's phenomenal. I'm sure that Sinan is also great. I just don't know them. Same with David, same with some other people. But Tyler and Leo are both people that I've experienced with. Robin, also someone I can highly, highly, highly recommend. Robin is a physics major who also took my 2848 class. She's phenomenal. Lots of people, lots of times, lots of availability. Go see them. One way or the other, you're going to have to spend time learning this material if you want to do well. This is going to make your time more efficient and more meaningful. If you don't believe me, try it, test it, you'll see what I mean. If you're going to solve the problems anyway, why not do them with someone around who can help you? Just pop on in. It's in PSV. It's right around the corner. The room's got, it's great. This is a great resource. So, plan around that. Go with friends. Solve the problems with them. You don't need to come in having questions. You can just come in and start solving problems, and then when you have questions, ask them. So, there you go. Resource, all that good things. All right, so last class we talked about voltage. And what I tried to convey to you all is voltage is like a height. Voltage is like a height. And so to that end, if you know how a ball is going to behave on a hill, you're going to know how a proton is going to behave in a difference potential. So I showed you all this picture at the end. This equipotential surfaces, if you like it. The equipotential map looks like a topography map. And the word equipotential, fancy word meaning equal potential, which I won't spend too much time on it. But yeah, think of voltage like height. Think of voltage like height. If you can make that connection in your brain, you will understand what voltage is. Voltage is not energy. Potential difference is not energy. Potential difference, voltage are two words that mean the same thing. Just like height is not energy. Height is not energy. Potential difference is not energy. How do you make it energy? You multiply it by the charge. How do you make height into energy? You multiply it by mass times gravity. You put something in it, and there's some gravity, and you got that. Great. So, we chatted about that, spent some time. There is one problem I wanted to make a notification to you on. This one, we saw for the voltage at the top. That was all correct. That was all fine. No problem. The potential at the top of this triangle where that negative 2q charge is located, that is 2kq over A. That is the potential at the top. Great. I then told you that the energy was negative 4kq squared over A. I took the potential at the top and I multiplied the charge at the top. This is not an incorrect statement what I wrote here, but what I want to do is clarify something. This energy I wrote here at the bottom is the energy required to bring this negative 2q charge into the system. So to kind of draw this out a bit, because I really want to make this clear. It seems like a small thing, but it matters. So if I have these two charges here, one positive charge in the bottom, another positive charge in the bottom, they make a voltage up here equal to 2kq over A. So this one's got charge Q, this one's got charge Q, and they're distance A from that. The thing I solved at the end was I said, let's pretend that we put a negative charge there. So I'm going to draw the same picture, but put the negative charge in. And the question basically is how much energy is required to bring a charge here? How much work is required? The energy required to bring this charge in, the amount of energy my system will increase is going to be that charge, which is going to be that 2q, specifically the negative. Negative 2q times the voltage there, which is that take 2kq over A. So I just multiplied Q times V. And so this is not, and this is the clarification, this is not the energy of the system. This is not the energy of the system. This is the energy just to bring this one charge in. Might sound like I'm saying the exact same thing, and that's where the nuance is, and that's what I want to emphasize. This is the energy just to bring this charge in. If you want the total energy of the system, I'll actually solve this out very quickly. If you want the total energy, you need to build the system. We did this in a previous PowerPoint slide. We bring in one charge. So the energy required is the energy required to bring in charge 1, plus the energy required to bring in charge 2. Plus the energy required to bring in charge 3. That is the energy of the system. It's all three. How much energy is required to bring in charge 1? 0, because nothing else is there. Then we bring the second charge in. How much energy is required to bring that one in? It's going to be kq squared over A. How much energy is required to bring the third charge in? Negative 4kq squared over A. So my total energy in the system is negative 3kq squared over A. There's a problem in the problem set there's one like this in the problem set. It's got different numbers and things like that. I think it has different numbers. But this is something I want you all to be able to do. Realize specifically that the energy of multiple charges is you got to add one charge at a time. You add a charge, then you add a charge, then you add a charge. And at every step, how much energy was added, how much energy was added, how much energy was added, then you add them all up.
So that's what the question was asking for, what you just did?
No, the question was just asking for the voltage, and then I just stapled on this thing at the end, and I wanted to give some clarification to what I stapled on. Yeah.
So the negative 4kq squared over A, that's the electric potential at the top of the triangle?
No, that's the energy, the change in energy. The electric potential at the top is just take 2kq over A.
Okay.
Yeah, the potential, remember that's like the height. The potential at the top is just 2kq over A. The energy required to bring this charge up here in is negative. You have to multiply it by that charge. Voltage is the height. Energy is you take that height and you multiply it by charge. Of the system, yes. This is the total energy of the system. Every extra charge we'd bring in, you'd have to add the energy to that to get the total energy of the system. So again, the analogy I connected this to you all, to help you understand this, when you charge a battery, every additional charge you bring requires extra energy. When I bring one charge in, there's no energy stored. Then I bring a second one, now I've stored some energy. Now I bring another one in, now I've stored even more energy on top of the original energy. Now I bring another one in, and I store more energy on top of that. Think of, you got the earth and a bunch of things. So let's say I've got my water bottle and this other bottle. If I raise this water bottle to a certain height, there's some energy stored. If I now bring my thermos to the same height, now I have more energy stored. What's my total energy stored? The energy for bringing the first one up and the energy bringing the second one up. And you add them together. Each one adds more and more and more and more. In this case, though, they're also fighting each other and all that jazz. So, anyway, something to think about. There's some questions about it, but I wanted to clarify that because I think I just kind of skated over it and didn't clarify well. Yeah?
So the total energy of the system is negative. Does that mean that forming the system actually gives you energy?
Yeah, that's a great question. Sorry to, but you're completely right. The energy at the end is negative. Why? This negative charge, I didn't actually have to I didn't have to apply an external force to add that negative charge. The positive charge has actually pulled it down. So this negative here means that it was actually easier to bring this charge in. Why? I'm not fighting anything. That negative charge wants to come there. So actually we reduce the energy of the system. What does the energy of the system mean? It means the system's ability to do work. This negative charge bringing in reduced the energy of the system because previously those positive charges wanted to fly away from each other. And they would fly away forever and you get a lot of energy released from that. Now by bringing this negative charge in, they all just want to collapse together and you're not going to get much energy released from that. So that's what's going on here. I've actually reduced the energy of the system. I've reduced the ability of the system to do work, to do something significant. They're not going to fly away anymore. Now they're all going to attract together and that's not as interesting as them flying apart infinitely far away. Yeah, energy is an interesting thing. All right, so just to keep things moving on, other reminders, we did this integral. Make sure this is a skill. I just made your all's quiz that's going to open tomorrow. You do need to know how to integrate the electric field. I even put it all in terms of vectors. You'll see what I mean when you open it. It's fine. On the quiz, I'm really testing if you know what's happening with this dot product and directions and all that jazz. You'll see when you see it. Did this problem, which way charges move, awesome, went to the capacitor. This one I'll kind of run through, it's very easy. And you're like, how is this easy? You'll see what I mean. A proton is placed in the positive plate inside a parallel capacitor with a potential difference of 100 volts across it. How fast will it be going when it gets to the negative plate? So, we always start with, what am I solving for? Velocity. We draw a pretty picture. We got some positive plates here. And then we got some negative plates here. This is what a parallel plate capacitor, it's the next thing we're going to learn about. And we place a proton here on the left side, and there's a potential difference of 100 volts across it, meaning delta V is 100 volts. And actually, there's something important I need to note here. Delta V is 100 volts. Yeah, that's fine. I'm going to leave that as is. But actually, let's put some numbers here because maybe that's going to make it easier. When I say delta V is 100 volts, it means the difference between the sides. I want you all to think for a moment. Delta V means there's a difference between the two sides. One side is higher, one side is lower. I want you all to think, don't yell it out. Think in your head which side has a lower voltage, which side has a higher voltage. Think about it. All right. So, which side has the higher voltage? The positive side. It's what you want it to be. The positive side's going to have a higher voltage. The negative side's going to have a lower voltage. Why? This side's negative. This side's... There's like a few ways to explain this. Remember, for a point charge, it's KQ over R. If Q is negative, it's a negative number. Negative 10 is smaller than positive 10. That's one way to think about it. Now, when I say this difference is 100 volts, I'm purposefully going to make this problem a little funky just to see if you're understanding what's going on. That means if this side is 100 volts, you'll be like, what? What's the other side going to be? Good. All right, great. You know what's going on. That's important. It's not 0. What's important here is the difference is 100. I don't care what values they are, as long as when I subtract them, it's 100. This is a hill. I don't care where this hill is located, as long as the top point and the bottom point are 100 different from each other. It's still going to be the same thing. I can make this left side 1,000,000, and then the negative plate would be 1,000,000 minus 100. When we talk about this, I don't actually, so, obviously it's easier if I made this 100 and I made this, or made the right side 0 and the left side 100, but you can choose any numbers. I really, really want to emphasize to you, this is all relative. It's all relative. But for the sake of making it weird, I'm going to use these other numbers. Rule of thumb, if I ask you how fast something's going on test 1, I can straight up tell you it's going to be conservation of energy. Guaranteed. That's just a rule of thumb. Why? Because there is no other way to solve this. The only other way to solve this would be integrating the work, the force done and all that, and that's just deriving conservation of energy. The force is changing. Well, the force is a constant action in this case, so it would be nice. But whatever. Conservation of energy. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. I then rearrange this, and I get that the negative change in potential energy due to the electric field is the positive change in kinetic energy. And you're like, whoa, how did that happen? Subtract the initial to the right side, final minus initial is positive. Subtract the final to the left side of the potential, initial minus final is the negative change. It's a good thing for you to look at and think about. So, great. What's the equation for the change in potential? It's just Q times delta V. Negative Q times delta V. And that's going to equal my change in kinetic energy. My thing starts at rest and it ends moving. So if I write this out, I'll be kind. My initial velocity is 0, so that term goes away. And then this is all fairly simple after this. Now, notice there's a negative sign. I'm actually going to rearrange this equation. So we're going to get VF equals 2 times Q times delta V, negative Q times delta V. There's a 2 divided by M, and then I square root it. And you look at this square root and say, I can't take the square root of a negative. There is no initial kinetic in this, because we're going to say it starts at rest. If you place something somewhere, we'll say it starts at rest. That's a good kind of thing to keep in mind. So, Q, this is a proton, so that's not going to get rid of it. The mass of a proton is positive, that's not going to get rid of it. But if y'all look at your delta V, and you actually think about what that represents, and now we're going to see why I wrote these numbers here. Negative 2Q, remember delta V is final minus initial. My final, the final that I made up for you all, is 100. My initial is 200. The delta is 100, but you have to know which end the high end in and which is the low end so that that negative cancels out for you. And boom, you plug this in, you get the answer, and that's, there you go. There's the answer. The math part's easy. What do you use for M? Mass for proton. What do you use for Q? Charge for proton. Plug in the things, easy peasy. What's really cool is we didn't care what happened between these 2 points. This is why conservation of energy is so useful. We didn't care how the potential varied between the 2 points. We only cared that at the beginning and the end, it was 100 different. So the analogy to you all is when you all did conservation of energy in Physics 1, you didn't care whether the hill was a big bumpy path or a straight line down. And this is why conservation of energy is so powerful. It lets us solve problems that would otherwise be disgusting. If you all remember doing the problems in Physics 1, you never did a bumpy, if you did a bumpy one, you did energy. It's not impossible to do with forces, but it would be miserable. The force of gravity the components would change constantly. It's awful. Yeah?
So you have the negative delta, the negative change in potential, and then it turns into negative Q change.
Yeah, that's a definition. That's the this is the definition, yeah. So this change here, this is the definition of the change in potential energy. It's Q times V. Q times delta V. That comes up in a previous slide.
Q times
Was
delta
that-
V.
Yeah, it's somewhere up here. Ta-da!
Q this one?
Q is the charge in the voltage.
Okay.
Yep.
So change in voltage times negative Q.
Yep. Well, delta U equals Q delta V.
Right.
Yep. Yeah. All right. Ready chatting about this? Now this is going to help prepare us for the next slideshow. Here I have I have two infinite planes. Positive on the left, negative on the right. Remember we talked about these equal potential lines, and I'll even remind you all, remember topography, the closer those lines are together, the steeper the surface. The closer they are together, the steeper the surface. The farther they are apart, the more not steep it is. So what does that mean? The steeper it is, the stronger the force. The stronger the force, the stronger the field. You all know that from topography. If you're like, look at this, the steeper it is, the faster you're going to get pulled down. Why? Because the force of gravity is going to be more in that downward direction. And we think of that fields cause forces. So, closer lines, stronger force. Stronger force, stronger field. Here's a picture of 4 different situations, and I say, which of the following is the correct equipotential lines for two infinite planes? Is it one where the equipotential lines start really close together and then get wider? Or they start really wide and then they get close? They start close, get wide, then get close again? Or they stay a constant distance the whole time? Think about it, and I'll punt it to your all's devices in just a second. All right, so I'm going to give you all a minute for this. Give you the reminder, closer the line, stronger the force. Stronger the force, stronger the field. That's the logic you need to answer this.
Is it a positive or negative charge
So, no charge is placed in it. This is asking about that height map, that potential map. No charge needs to place in it for that, because these are the ones making the potential map. Yeah. All right. Give me even extra time. Give me 10 more seconds. All right. In 5, 4, 3, 2, 1. Yeah. So you need to. So remember the logic. I walked you all through this. The closer the lines, the stronger the force that would be experienced. And if there's a stronger force, that means there's a stronger field. So the long story short is closer the lines, stronger the field. More distant the lines, the weaker the field. That's the logic here that we're going to use. So it'd be very, very useful if we knew the electric field due to an infinite plane. The electric field due to one infinite plane is sigma over 2 epsilon naught. You're like, whoa, where did that come from? We derived that previously. That's an infinite plane. We use Gauss's law. It's in the problem set. It's a very useful one for you all to know. Very, very useful. It's going to show up in the next PowerPoint a lot. So, through the magic of having 2 infinite planes, So the positive one's going to make a field to the right. The negative one's going to make a field to the right. Through the magic of having two of them, they add together. So if you have two infinite planes, we just get, a 2 on top, and it cancels out that. It's twice as big. If you have two infinite planes that are opposites in between them, the fields add, and you get twice the field. Great. What's the takeaway here? This is the charge density. The charge per unit area on the planes. Epsilon naught is a constant. Everything is a constant. Q is a constant. A is a constant. Epsilon naught is a constant. What does that tell us about the electric field? Any distance away from an infinite plane, it's a constant. The electric field is the same everywhere in between it. So if I drew the electric field really close to it, it's the same size as if notice all these arrows are the same size. The electric field is the same everywhere. And like I told you all, the distance between the equipotential lines gives you a sense of the strength of the field. Closer line, stronger field. Farther apart, weaker field. If it's the same everywhere, then my line should be the same distance apart everywhere. If we think of this like a map, if we think of this like a height. So, to connect this to height, if I draw a graph of what this height looks like, if it's a constant, we get this linear slope, there you go, that's what the height map looks like. Height map, potential map. Yeah.
I thought though, it would be C because the further away you got, the weaker the field.
That would be true if the electric field cared about distance, but it doesn't. The electric field, due to an infinite plane, does not care about distance, does not care about how far away you are. It is the only geometry I'm familiar with that has that rule. It is a very special thing about an infinite plane. The electric field does not depend upon how far away you are. It is a constant everywhere. Then it would be a different story. If it was finite, it would actually be very similar to D. In fact, all real-world capacitors are finite. But they're close enough together that they're effectively infinite. They don't see the edges.
So since it's equal charges, each arrow should be the same.
Since they're equal and opposite, the fields add together. That's more so the thing. So we'll chat about this more in the next PowerPoint. We're going to derive this thing I put up here on top. This depends upon how the field, and this is checking, do you know what the field looks like due to an infinite plane? It does not depend upon distance, which is a fantastic segue into our next PowerPoint, which is all about infinite planes together, capacitors. Yeah. If they're the same sign, that's a great question. They'd cancel out everywhere, and the field would be 0 inside. Yep. Ooh, look at those different answers. Great. All right. I'm not going to have you all do this next slide, but just to kind of go backwards. So a reminder to you all, if the voltage is defined as the negative integral of E dot ds, what's the opposite of doing an integral? A derivative. So if you kind of rearrange this, you can instead write the electric field as the derivative of voltage with respect to space. If you take the derivative across all 3 dimensions, we call this a gradient. You've probably seen it or are going to see this in physics or in Calc 3. What does the gradient give you? It gives you the slope. Think of height. The steeper the slope, the stronger the field. The steeper the thing, the more gravity is affecting something on the hill. So this is something for physics majors. This is very important for probably electrical engineers as well. I'm not going to have you do it because technically you haven't taken Calc 3 before this, yada, 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 whatever. But I wanted to show it to y'all, that it is significant. And it's something we've been saying conceptually, but I'm not going to have you do this. It is very simple, but whatever. All right. Last question. How do we create these electric potentials? We've been talking about them. We've been saying hypothetically, put a charge here, put a charge here, put a charge here. How is a good question. It's one thing to say I'm going to move this charge here, but how do I actually do that? There's a few ways to do it. So lightning is one example. Lightning results because of a separation of charges, but why is there a separation of charges is a little bit more detailed. So, 3 mechanisms. We're going to talk, there's a few. It's just good to kind of mention them. You need to separate positive and negative charges. Like to make a potential difference, you need to separate them. You got to get some more positives here, some more negatives here. Generally by moving negatives, but you can move positives in the case of batteries. So 3 ways. One is something you all did in your first physics lab during that. It's literally rubbing some mechanical separation, static electricity. When you all rub your feet on socks, you are taking charges, either you're transferring or giving them, and that's complex for which is happening. You have a balloon on your hair, same thing. You all rub the rods with the cloth. You can transfer charge literally through mechanical connection. You may be like, why does this matter? So what? Static electricity, not a big deal. Some huge examples of this that are very relevant for you all. So I mentioned the graph, whatever. I'll chat about that in a second. Your car tires are conductive. Something you might not have thought about before. Something you've never considered. Something I hadn't considered until recently. When I was watching the video about rubber and all that jazz. It's done by Veritasium. Great video. Anyway, why are your tires conductive? What are your tires constantly doing? They're rubbing against the ground. Why does that matter? They're constantly going to be building up charge. If your tires were not conductive, that charge would build up a ton on your tires and would be very dangerous because they're constantly rubbing against the road. So that's something you might not have known. Most people don't know. Another example of this was the aforementioned lightning. How is lightning generated? A separation of charges. Why are these charges separated? Literally, the air molecules and the dust molecules bounce into each other. There's collisions in the atmosphere and the clouds. Those collisions separate charges. You get a giant amount of distributed charges. Eventually, it gets so big that air becomes a conductor.
With the car thing, is that why they say like when you fill up your gas tank, it dissipates static?
That's more so just from you, less from your car. But yeah, that's, gas is flammable, a static, yeah, that can ignite it. But it's very unlikely. You're not going to get that much. All right. Yeah. So that's another one we're going to, that'll be the third one. Yeah, it's a great kind of foreshadowing of something for test 2. Batteries do chemical reactions. How do you separate charges? Through chemical reactions where things want to take charges or lose charges through the chemical energy stored. To store this energy, you convert it from one other type. It's chemical. We're not going to get into the mechanism, but again, I think it's, I don't remember who. It might have been Veritasium as well. I had a great video about lithium-ion batteries, which is very interesting and talks about that mechanism. Generators is the last one. This involves magnets. And this is where we're going to learn, and I'm going to use a bunch of fancy phrases here. If you have a changing magnetic flux, it generates a change in voltage. Magnetic flux sounds maybe fancy, but you've already learned about electric flux. Just replace electric with magnetic, and it's the same idea. If you have a changing magnetic flux, we're going to learn it makes a voltage. And that voltage drives current, and that's how generators work. So, great. I don't need you to know all 3 of those things. That's just fun facts for you. That's relevant as we kind of chat about future things. So through the power of saving this PowerPoint, I'll upload it after class, and then we're going to go into capacitors. Because my goal, so for the test upcoming, I need to teach you all about capacitors, and then I'm going to teach you some amount about current and resistance. We might not get to current, but we'll definitely get to resistors. So we'll chat about capacitors today, and it likely will slightly roll into Tuesday, almost guaranteed. So, capacitors. The name tells you what it does, kind of, sort of. What is a capacitor? It's something that has capacity. What does it mean to have capacity? It means you can hold stuff. What does it mean? What are we holding? Charges. It's in the name. Capacitors are things that have they have capacity. They hold charges. So, background on this. This is, well, I guess we'll talk about what they are, their function. We'll talk about their connection between voltage, current, voltage, charge, energy stored, series and parallel. We're going to define what series and parallel means. It's going to be similar to what you're familiar with, but parallel is going to be different in some ways that are important, and then how to combine them. So these are the things you need to know. We've seen some, this is literally all in the last PowerPoint slide. You need to know the electric field for an infinite plane is sigma over 2 epsilon naught. Just saw that. You need to know the relationship between voltage and electric field, where it's the integral of E dot dr. I believe, though, I'm missing a negative sign here, so that's a typo. Boom, through the power of putting it there. Great, now it's fixed. And the energy stored is Q times V. Cool. We're going to use those throughout this PowerPoint to derive and understand things. But these are all previously listed equations. They're not new. All right, so first capacitor. You don't need to know this, but it's fun facts. It was called a Leyden jar. And this is way back when they're first experimenting with charge, they needed to store charge. If you want to do experiments with charge, you got to separate it. You got to build this electric potential. How do they do it? By rubbing stuff together. Then they needed a place to store that charge so I could build up a bunch of it. So they came up with this Leyden jar. It's a very, very, very simple device. It is a glass jar filled with water. On the inside is a piece of like aluminum foil, and on the outside is a piece of aluminum foil. So if you imagine this side here, it is 2 infinite plates separated by an insulator. That was the first thing. Sure, it curves around, but on each side they're basically like 2 infinite plates. They were discovered independently by 2 different people. Kind of interesting. German cleric. I looked it up. I was like, cleric. He's like the president of some, I think that's a phrase they use for some chapel or something like that. I don't know, interesting things. It's always interesting seeing who's doing science throughout history. It varies on who's able to do it. It usually requires either someone's got to fund you, so who's funding you? And a Dutch scientist. They did it independently around the same time, 1745. It was for historic charge, so they could do experiments. You can't do any experiments and measure things unless you have a way to build this potential. And last thing is this, there's this little conducting rod, and all that does is just connects to the interior plate, so I can add charge up here and have it distribute to the charge down there. That's the whole point of that. Great, exciting. It's good to know that it's just interesting. I didn't know this before I did it. So, fast forward a bunch, and it is still useful for us to store charge. How do we do it? We get 2 infinite plates. We put an insulator between them. The reason we put an insulator has 2 purposes, one of which is just so that the charge doesn't jump across it. You know, if these 2 plates touch, say this one bent a bit and touched that, well, all the charge is going to just go to that plate. It's not going to stay separated if it has a way to get to the other side. So you need a way to keep them separated. How do you keep the charges separated? Put an insulator in between them. But not only does that help keep the charge separated, it also boosts the amount of charge you can store on these things. We're going to talk about that at the very end of this PowerPoint, how an insulator actually adds to the amount of charge that you can put on these plates. We call it dielectric. Yeah, and so you're not going to find any capacitors out there that are big old rectangles that take up a bunch of space. How do we make it more efficient? We roll them up. You take these 2 infinite plates, you put an insulator on them. You also put an insulator on the outside here so that you can then roll it up like a carpet in your home. No one's storing carpets in a big old square, like you roll it up to take up less space. So that's all the capacitors that you'll see out in the wild. So if we just look up one, I have pictures later on. Capacitors. This is a very useful device that is present in almost every single electrical device that you own has capacitors in it. They're cylinders because they took these things and they rolled them all up. Bunch of different sizes. There is some like flatter ones. I honestly don't know exactly what's going on there, how they did those ones. But yeah, they generally are cylinders and they're wrapped on up. My example to you on the practicality of knowing about capacitors is your AC unit has a capacitor, and this is one of the most common things to fail in an AC system. And this is extremely easy to diagnose and replace. Like every single one of you, through watching a 5-minute video, could do this. And it's a capacitor. It's a big, chunky kind of thing. It's about the size of like a small Red Bull container. But you can then go buy one at Ace Hardware. You get the right one. Great. And why do I know this? Because I had to fix my own AC system at some point. It took me 20 minutes. It was awesome. Saved me $100 to $200 paying someone. Each of these costs, $20 at a hardware store.
When you charge your phone or something, is that electricity going to a capacitor?
It's a good, it's a battery, which is different. Yeah, which may sound obvious. One of the future goals is that they can build capacitors that could do a slower trickle. So no, but it depends on your application. So what do we use capacitors for? That kind of segues us into that. Anything where you need a lot of charge really quickly. So the way I describe capacitors is think of them like a bucket. If you have a hose, your hose is your battery. Your battery can only output so much current. That's the water coming out of it at a time. No matter how much you turn that dial on your hose, it's only going to come out so quickly. But what if I want a ton of water really quickly? I fill up a bucket. What's the magic of filling up a bucket? I can then take that bucket after a bunch of time and dump it and release all that charge, all that water very quickly. That's a capacitor. A capacitor is something that you can slowly fill up, get a ton, and then release it super quick. What are some applications of this? A stud finder is one. That one you're not releasing charge. We'll talk about that. A car amplifier is one where you need additional charge. So if anyone's ever done anything with a sound system, subwoofers require a lot of current in a short period of time. So if you have a big old subwoofer and you have some bass in your song, that requires a lot of current, far more than your car battery can output. How do you supplement that? You have this capacitor that you can basically kind of siphon from when you need it. It can slowly trickle when you don't. It can slowly charge when you don't need it. And then when you do need it, it siphons off that charge. That's an example of it. Lightning is a capacitor. You build that charge, it discharges defibrillators, same thing. They charge up the defibrillator, get a bunch of charge, and then they inject that into someone's body very quickly. Phone touchscreens use capacitance to determine where your finger is. Old-fashioned camera flashes. This is before your time, probably. Way back when. I mean, if you buy a disposable camera, I don't even know if people buy those anymore. Again, this is back when I was growing up. There's a little thing that whenever you did a flash, you'd like flip this little thing, and this little thing would then charge up your capacitor, and then when you click the button, it would discharge the capacitor and make the light bulb flash. Yay. And basic circuitry also uses capacitors. It also helps you regulate your flow of current, whether to keep things a bit steadier, but that's a future thing. There's things called high gain, low gain. There's filters, different filters, and they use these. We're not going to get into that in this class. All I want to convey to you is they're super useful. This entire PowerPoint is more engineering than physics, but we're going to use the physics to derive the equations for the capacitors. Yay. So, what is the definition of capacitance? If we think of it, the capacity to store charge, that's where the equation comes from. How much charge can I store per unit voltage applied? More voltage means I can store more charge. So we divide by that voltage to kind of normalize it, standardize it. So for every 1 volt that I apply to it, for every 1 volt of potential difference, how much charge can I put on this thing? That's what a capacitor is, just a definition. It's almost like I use like a tire. For every unit of pressure I apply, how much air can I stick in this thing? More pressure, more air. Bigger tire, more air. The unit is farad, named after Faraday, one of the people that did a lot in the background here. The symbol for it is capacitance, so in equations in C, when you write down the capacitance, though, if you want to say how much capacitance, you would say farad. Now, 1 farad is a ton. 1 farad is a ton of charge. 1 farad means if I apply 1 volt, I get 1 coulomb. 1 coulomb is a lot of charge. I mentioned that way back when. It is far more likely when you all look at capacitors that you're going to be working with microfarads. That's just more common. For example, the AC capacitors are in microfarads. Y'all, I think mine was like 26 microfarad or something like that when I bought it. So, this is just the definition based on what it is. How much charge can I store?
How many farad is 1.3 watts or whatever it is? Never mind.
Yeah, okay. So, let's see if y'all remember this. Fingers crossed you do. What's the equation for the electric field due to an infinite plane? Is it sigma over 4 pi epsilon naught r squared? Q over 4 pi epsilon naught r squared? Sigma over 2 epsilon naught, sigma over epsilon naught. Give y'all a whole minute. All right, 10 seconds. And 5, 4, 3, 2, 1. All right, it showed up in the one of the first PowerPoints in here. Ta-da! It's sigma over 2 epsilon naught. We did. So there it is. But if you don't know it, that's all right. Now hopefully you do. All right, we're going to build a capacitor. A capacitor doesn't just have 1 plate, it has 2 plates. So what if there's a second plate? I'm not actually going to open this question because I don't want to spend the time on it. But just remind you all, the positive plate makes a field to the right, the negative plate makes a field to the right. through the magic of adding them together. So one makes a field that's sigma over 2 epsilon naught. The other makes a field that's sigma over 2 epsilon naught. We add them because they're in the same direction. Through the magic of adding, the 2's cancel, and we just derived the equation for the electric field in a capacitor. Easy.
Why do they go the same direction? I thought
Great. Fields, do they point away from positives or towards positives?
Away.
Fields, do they point towards negatives or away from negatives? Towards. So we got a field pointing away from the positive, we got a field pointing towards the negative. It's a good reminder. All right. Boom. Answers. Great. Didn't do this one. All right. I have the utmost confidence in you. Now we're going to derive the voltage. We just derived the electric field in a capacitor. In fact, I'll write it again up here for you. In a capacitor, the electric field is sigma over epsilon naught. My question to you is, I have the following situation, a negative plate on the left and a positive plate on the right. I want to find the potential difference across them. Through the magic of memory, I remember that the equation is delta V equals negative integral of E dot dr from initial to final. E is the electric field, dr is the direction I'm moving, I is where I start, F is where I end. I have these plates with a charge Q and an area A and a distance D apart. Go ahead and derive the expression for the voltage between them. Is it Q over A epsilon naught, A over Q epsilon naught, QD over A epsilon naught, or Q over AD epsilon naught? I'll give you all 2 minutes for this one. Very generous. You're gonna want to write it out just to make sure. Like, don't the integral. Actually solve the integral. If you're not doing the integral, you're not doing it right. Write it out. The more you try to store in your head, the more likely you are to make a silly mistake and also not understand what you're, when I eventually show it what's going on. Write it out. All right, since it seems like people are still diligent working, I'll give you to 2:30. So 40 more seconds. All right, we'll go 20 more seconds. Let's get more time to keep things moving. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, so let's solve this integral. Let's build this integral. This is a skill that we're working on, is being able to build these integrals using physical pictures and problems. So I start with my integral. Negative from initial to final, where that's my location. Electric field. This is a dot product. So we're going to unpack this dot product. Remember, a dot product is written as the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So we need to draw some arrows. We need to draw the direction of the electric field. The electric field in this case is going to point to the left, away from the positive towards the negative. That's why I put the negative on the left side to help out with that. The colors are all the same on this. It's fine. Oh, yeah, I tend to do that. It's fine. Don't worry about it. That was just a typo, not typo. Yeah, generally we do red is positive, blue is negative, but whatever. All right, we're moving to the right because we're going to go from the left side to the right side. I say that somewhere in this problem would move from the negative to the right, the negative to the positive. So, what's the angle between these? 180. Why does that matter? Cosine of 180 is negative. That gets rid of that negative sign for us. How nice. Yeah. Now we're going to plug in the electric field. Sigma over epsilon naught. Gave that to you all. We're also going to change dr to a variable that's maybe a bit more like matches this one, just to help us understand it. Which one am I moving? Up, down, or left, right? So we're going to use dx. Remember that dr is just an arbitrary path that you're taking. It's useful to sub in the actual, to help you understand what you're integrating. It's helpful to sub in. In this case, we are going from left to right. We're moving in the x direction. Just helps you keep track of what you're doing. Because now we're integrating over x. So what's my initial coordinate? So this is something interesting. I didn't specify a coordinate system, but it doesn't matter. I told you the distance between these is 2D. So I could do something really weird. I could say that I start at 3D and I end at 4D. You're like, what? What's going on there? All that you care is that the difference between them is D. I start somewhere and I move how much farther? D. So I'm not going to leave that there because that's going to confuse more people than it's worth. But I do want to mention it. We'll go from 0 to D. It's the same thing. It's all relative. Distance is all relative. Your origin, wherever you choose to do it, doesn't change anything. So through the magic of plugging this all in, we have negative integral of sigma over epsilon naught times 0 to D. 1 second. Once I write it out, all will become clear. The negative 1 from the cosine goes there. Boom, negatives cancel. And then we have the integral from 0 to D for sigma over epsilon naught dx. Super easy integral. Sigma is a constant. Epsilon naught's a constant. Yank them out of the integral. So we get sigma over epsilon naught times x evaluated from 0 to D. That's going to be sigma d over epsilon naught. And you're like, that's none of the answers. Then you need to remember sigma is defined as q over a. And there's your answer. It's q over a, well, q times d over a epsilon naught. And this is the electric potential across the capacitor. Now we're going to do another step with this. Again, it's all stacks. Yeah.
Where's the sigma?
Definition. Great question. Remember to y'all, what is sigma? Sigma is defined as my charge density, my surface charge density. It is how my charge is distributed over an area. We could have subbed that in at the very beginning if you had wanted to. You could have done it at any point. All right, so what? Remember, everything I teach in this class stacks on each other. We're now going to use this. How are we going to use this? Well, remember the definition of C is Q over delta V. Where did that come from? That's the definition of capacitance. We talked about that a few slides ago. We just derived delta V. Q times D over epsilon naught and an A. We just derived that in the last slide. Through the magic of taking this and plugging it in the bottom. We're going to derive capacitance in terms of area and the distance between the plates. So now we're just going to plug that in. So we have a Q on top, and then we have Q times D over A epsilon naught on the bottom. Keep flip change. Q's are going to cancel, and this is going to equal A over D epsilon naught. The A gets flipped to the top, the D gets flipped to the bottom. The epsilon naught stays on, goes to the top, if I wrote that right. That's why it's good to check your work. Yeah, thank you. Yeah, notice that someone. I always look at your eyes. If there's like a confusion look at people, it's like, okay, they're missing out. Epsilon naught goes on top as well. If you want to see that a little bit easier, it's right there. And we have derived the expression for capacitance. How much charge, so how is this capacitance determined? The bigger the area, the more space I have to put charge. So I can put more charge on it. The closer my plates are together, the more charge I can also put on it because it'll kind of pull more charge. They're equal and opposite, so when they're really close together, that's going to kind of help out. Yeah. Oh, that's, area times epsilon naught over D. And that came from the last slide. Yeah.
What do you mean by area? Area of what?
Area of the plates, of these infinite planes. So I keep telling you they're infinite. They're not really. We're not out there building infinite planes. But if you put two infinite, so the analogy I give to you all, does infinity exist? What a great hypothetical question. As far as we're aware in this reality, infinite doesn't exist. If you ask about the supernatural, that's a different story. But approximations. If I stand really close to this wall, such that my face is super close to it, I don't see the edges anymore. If I can't see the edges of a plate, it's effectively an infinite plane. So, that's we're able to use this approximation, and it's pretty darn good. These plates are super close together compared to the area of them. So, ta-da, there's the equation. It's the same slide as before, but now we have our updated definition of capacitance, epsilon naught A over D. Bigger area, more charge. Closer together, we can also put more charge on them.
What if the area of the plates are different?
That's a great question. What if the areas of the plates are different? Then we don't do that problem. I honestly haven't seen the derivation for it. My guess is that it would probably change things, but generally we keep the plates the same size. Yeah, that's a great question. Because the extra plate from the other one just wouldn't really add that much to it. If you could fit the extra area from the one, you could fit the extra area from the other. Yeah.
So D just tends to be this structure.
Sorry, what was that?
D just tends to be this structure.
Yes, D is the distance between the plates. D is the distance between the plates. So you can kind of see that on this picture, though it's kind of small. D is the distance between the plates. Area is the area of the plates. They both have the same area. They're a certain distance apart, and they have equal and opposite charge. And that's a capacitor. All right. Let's practice this equation. Now, I'm going to mention this now because it's going to come up a bunch. So capacitance is purely a geometric quantity. It's purely dependent upon how you build this capacitor. How big are my plates? What's the distance between them? This is why when you go to the store, you can buy a capacitor and it tells you its capacitance because it's based on how big is the area, how far apart are the plates, and there's something else we'll eventually learn, what dielectric is placed between them, but that's at the end of the PowerPoint, one step at a time. So, what happens to the capacitance? What happens to about how much charge I can store if I half the distance between the plates, but I double the surface area? So these are those questions I like to ask where, hey, you've seen the equation. What happens to something if I change other things? Do I get the same capacitance? Do I get half the capacitance? Do I get double the capacitance? Or do I get quadruple the capacitance? All right, give you all 30 more seconds. And 5, 4, 3, 2, 1. All right, we haven't done one of these in a little bit, so I'm going to remind you all the technique. Remember, we write the original capacitance, epsilon naught A over D. That's the OG capacitance. Nothing's changed. Then we write our new capacitance, epsilon naught stayed the same. My area doubled, so I put a 2 in front of it, and my distance halved, so I put a 1/2 in front of it. I then pull out all the constants that just got added to it. I pull the 2 out. I pull the 1 over 1/2 out, and through the magic of multiplying them, there you go. It's 4 times bigger. And I think the answers here looked pretty good on this. Yeah, it's pretty straightforward. How would I make this more complicated? Maybe I say I want to get the capacitance 5 times bigger and I make the area 3 times bigger. What do I do to the distance? And you just rearrange the equation for distance and do the same process. So great job, great job. Now we're going to get into actually putting them in circuits. We're not going to get too much into circuits. So here's a battery. A battery is one way to make a potential difference. Remember, we got to charge this capacitor. To charge this capacitor, I need to actually force charge on it. How do I force charge on it? I have some device, something that makes a potential difference between the two ends. One end gets a high voltage, one end gets a low voltage. That will cause the charges to move accordingly. So, this little simulation here, I'm going to go ahead and open. This is a super useful simulation when we eventually get to circuits. Yeah, FETS is awesome. FETS lets us see things that you otherwise couldn't see. You can't see charge moving, but through the magic of a simulation you can. And I'll zoom in on this. So we're going to have, don't worry, I'm putting in a resistor. It's just to slow things down. We're going to learn about resistors eventually. I'm just putting it here to slow things down. Obviously, I haven't taught you what a resistor is yet, but you could just think about what the word sounds like. Resistor, it resists. It's going to slow things down, which is useful for us. So right now, nothing is happening. The capacitor has no charge on it. Why? Because the switch is open. Great, I close it. Oh, still nothing happens. Why? This battery is making a voltage of 9 volts. What does that mean? It means one side is 9 bigger than the low side. So this positive side, let's say, has 9 volts. The negative side has 0 volts. So everywhere connected to this negative side is 0 volts. So this is just flat ground right now. It doesn't see the high point. Until this wire is connected, it doesn't see the high and the low. I got 2 plateaus that aren't connected. Nothing's going to happen. So I'm going to disconnect this just so I can do it when I want to. Connect this. Still nothing's going to happen. All I've done is made this entire side 9 volts. There's a gap. It doesn't see the low end. And then I think I can, yeah. So you can then connect this, and what you'll see, oh, actually, yeah, this is fine. You'll actually be able to see the charges moving. So you can see these negative charges are moving very slowly. It almost looks like they're not, but trust me, they are. And the negative charges are building up on this plate, and in turn, they push away the negatives on the other plate, making it positive. We're not attracting positive charges. You can't move positive charges in a circuit. Those are literally protons that you'd be moving around, atoms. So you build up one side with negative, and in turn it pushes away the negatives on the other. The electrons float through the circuit, yay, you charge your capacitor. Now, what's useful about this is when I disconnect this, it's still charged. I have stored that charge in there. I filled up my bucket. What could I do with this? Again, this is something we'll see in the future. If I then had another circuit connected to it, right now nothing's happening. I'm going to put a switch on it. I'm going to open up this switch so that it can't flow that way. We're going to eventually learn this is called an RC circuit, R for resistor, C for capacitor. So I now have this other circuit. When I connect this, I can discharge that capacitor and do something with it. So this is the mechanism of charging a capacitor and discharging a capacitor for some practical application. Yeah.
Why does the simulation have like dollar bills and
Oh, just for silliness. Just for silliness. Yeah. Just for fun. Look, this is useful at all levels, high school, elementary, all that. So you can do silly stuff to keep people engaged. All right. Something I want to note here is that what is charging this capacitor? The battery. So to draw this out, if I connected this, so remember I told you all, let's pretend this is a 9-volt battery. That means this side is 9 volts. This side is 0 volts. Everywhere on this wire is 9 volts. Everywhere on this wire is 9 volts. Everywhere on the bottom wire is 0 volts. So what's my potential difference across my capacitor? If one end is 9 and the bottom end is 0. It's 9. How does that compare to the voltage of the battery? It's the same. If a capacitor is the only thing in a circuit, it will get the same voltage as the battery. if it's the only thing in a circuit. If there's other things, it gets split up. We'll chat about that eventually. This is very important to answer the next question I'm about to give you. So let me pose this question to y'all. Two capacitor plates separated by a distance d are connected to a battery with a potential difference of V naught, some arbitrary voltage, 9, 10, and 6. If the plate separation doubles while still connected to the battery, what is my new potential difference across the capacitor? Is it half the original? Is it the same as the original, 2 times the original, or 4 times the original? What do y'all think? Give it a spin.
What makes a capacitor explode?
You put too much voltage on it, if you put too much charge on it, so like, why is lightning happen? If you build too much charge, eventually insulators no longer stays insulated. They become conductors. You put enough voltage, air, which is an insulator, becomes a conductor. You put enough voltage, there's a little bit of plastic membrane becomes a conductor, and all that charge releases very quickly, causing a lot of heat and a lot of energy release, and a very resistive element. All right, give y'all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right. So to answer this, there's a couple ways. I'm going to do the quick one. You can do it with a simulation too. If you go to this example, I didn't tell you how far apart they were, and I told you got the full voltage of the battery. So if I change that, nothing changes. If this is true of some distance between the plates, it's true of any distance between the plates. A capacitor connected to a battery, if it's the only thing in it, it gets the full voltage. I don't care what kind of capacitor this is. I don't care if it's a 1 farad capacitor or microfarad capacitor, it gets the full voltage. What will change is the amount of charge stored on it. The charge will change if I double that distance. The capacitance will change. But the voltage is still going to be 9. You're still going to get the same voltage. And I can kind of show you all that in this simulation. If I get rid of this resistor and I connect this and boom, it charged super quickly because there was no resistor to slow things down. What I want to show you all is that if I take this and you can change the capacitance of it. If I make the capacitance smaller, I made the distance between them. That's the same thing as changing the distance between the plates. If you take a multimeter and you actually did this experiment, so it's 9 volts, changing the capacitance doesn't change that at all.
So capacitance is distance?
Capacitance is based on the distance in the area of the plates.
Right.
So, if you're connected to a battery, what determines the voltage? The voltage of the battery. If I didn't change that and I'm still connected, then all is well.
If you're plugged in like a wall.
Same, you got AC voltage there, that's more complicated.
This is DC.
DC, yeah. All right, so there you go. This is a nice summary of that. And then I have 3 last questions that I hope to get. I can get through them. Actually, I have 2 last questions for you all that basically test if I change something, what stays the same. So we've done one of those now. If I keep it connected to a battery, but I increase the distance, what changes? Or what stays the same? The voltage.
So looking at the equation, it's the charge times the distance on the top. So you said the charge changes, right? Is that why?
That's why. Yeah, great question. So his question was, the equation for voltage, though, is QD over area epsilon naught. I believe. I think I'm in the right spot. Yes, the distance halved, but the charge will also change. Or I think the distance doubled. What did I say? If I double the distance, I'm going to get half the charge, so those two will cancel each other out. Yeah, it's a great question. Because you look at this, say, but the equation has a D in it. Yeah, but it also has Q, and Q will change. You will get less charge on it. So how do you know that this is true? If you're connected to a battery, that's what's giving it the voltage. Why does this capacitor get any voltage at all? Because it's connected to the battery, and it will get the exact same amount as the battery because that's what's charging it in the first place. It will reach equilibrium with the battery and then stop. So, 2 more scenarios for you all. These are all what stays constant. We just looked at one of them. Another one is what stays constant if I charge a capacitor with a battery, disconnect it from the battery, and then double the distance. So the difference here is I've now disconnected it from the battery, whereas prior it was connected to the battery. So if I charge it, disconnect it, double the distance, what stays constant? Is it charge, voltage, or capacitance? And to clarify, no equation is going to tell you this. It's all conceptual. Equations aren't going to give you the answer here. All right, give you all 10 more or 20 more seconds. All right, close it out in 5, 4, 3, 2, 1. All right, so how are we going to answer this? I'm going to use a simulation because it lets us see the things I'm going to say as I'm saying them. So I charge this capacitor. And actually, I need to make it so I can actually half the distance. So great, I move it real close together. Awesome. I then disconnect it from my circuit completely. It actually wouldn't matter if you left half of it on there, but just to make sure that you're like cool with it being completely disconnected. When I then double the distance between the plates, my charge doesn't change. Why? Where is it going to go? It's stuck on there. I doubled the distance, but that charge can't get to the other side. Where is it going to go? I don't care. You can take those 2 plates of a capacitor, take one and ship it to Norway. They're still going to have the same charge as long as they don't discharge. They're stuck unless you give a path for it to discharge. Now, this is a great safety lesson for you all. And I got one more question after this. You can crank it in there. If you all are ever working on a capacitor, say your AC capacitor, say you disconnect all the breaker lines and all that, discharge the capacitor before you touch it. Just how do you discharge it? You put a piece of metal between the positive and negative terminals of that capacitor. You give a conducting path. You short it. You take a wire. You take literally a wrench. You take any piece of metal and you connect the 2 ends together such that it can actually do that. That is how you make sure that you are not the thing shorting it, and that the electricity doesn't fall through you. All right, great. That's charge. And then we're going to quickly do the last one. I know it's tight. Depends how much charge it is. Depends how much volt. There's a lot of variables there. All right, what stays constant? If I charge a capacitor, disconnect it, use it to light up a light bulb, and then I throw it across the room and don't damage it. All right, we're not going to spend long on this. We'll go to 40 seconds, so 30 seconds, just so I fit within my 1-minute window. Is it charge, voltage, or capacitance? All right, 10 seconds. Take a guess. 5, 4, 3, 2, 1. All right, what stays constant? The capacitance. Why? You discharged it. Charge is no longer constant. It's no longer connected to the battery. If I go and buy a capacitor from the store, it better be the same value as when it's shipped from China or wherever. Capacitance is based on the geometry. It should be the same if you don't change the geometry.
Professor, what's the voltage in the question?
All right. Hello, everyone. Sorry for the delay. I had to send out a few announcements. Obviously, you all got one of them. It has all the details in it. Feel free to check it out. But again, if you're uncomfortable being on campus, feel free to do it remotely. Feel like I'm already here. I'm not going to be offended if you walk out or anything. You'll see what, yeah. If you're not sure what I mean, look, I'll just read the announcement. In case you're like, what's he talking about? Get introduced to the fun of today. So yeah, I'm just going to read what they say because then it's clear. They always do a good job of these things. So UCF PD sent an alert saying the following. UCF PD is aware of a recent email threat received by many in our community. At this time, we do not consider the threat to be credible. All campus operations normal. Threat response management teams currently investigating, work with the FBI. Similar messages have been reported at other universities around the country. UCF PD patrols campus 24/7, ensure your safety. If you see somebody say something, I call 911. So, all that to say, there you go. There's the details. Given their response, I felt comfortable continuing to have class in person, but we're not going to do the lab that we were going to do today. We'll do it Tuesday. So we'll have 2 labs next week, one on Tuesday, one on Thursday. Pacing-wise, it's no problem. We're going to be fine. We're actually, and the reason I say that is we're an hour, 20 minutes ahead of my lecture class. Yeah, hour, 20 minutes. So we'll finish up capacitors today. When we finish, that'll be it for today. Normally we do the lab after that, but we'll finish capacitors and then we'll be done. Give you all some time to do whatever. So we got a little bit more with capacitors to go through. I have uploaded the PowerPoints for those. I had forgot to do it previously, so apologies on that. This is the wrong one. And a reminder to y'all, quiz 3, do this Saturday, all the good stuff. Also, I want to mention, so last class I mentioned my office hours, and that, I had a ton of people on Tuesday, and I was like, that was great, love it. I want lots of people in my office hour, but I was like, oh, maybe they'll get full. Wednesday, I had 3 people. So all that to say, my Monday and Wednesday office hours have a lot of, why did I have so many people on Tuesday? It's right after my lecture class, and it's right before this class, so there's the convenience factor. But if you're available Monday or Wednesday, I tend to have less people. You're going to get a bit more of my attention. And again, you all can come in and just, work on things. You can literally work on the quiz during my office hours, and I will assist you. With the caveat that I'll have at least one of you have done the quiz once before on your own. That's the caveat to that. But that's to show you that I'm willing to help you with anything, even the quiz problems, as long as you've at least tried the quiz yourself at some point. It will not do you, the quiz will not do you a ton of good if you have someone helping you the entire time. Because remember, the point of the quizzes is for you to see, do you understand the stuff? And if someone else is helping you, you're not really determining if you know it. But they are good problems. I made the problems. I spent the time on them. Making good problems takes a lot of time and effort. I try to spend that time and effort, all that good stuff. So.
Someone's texting me asking if you started the live stream.
I did start the live stream. It's on.
I'll text them back.
Yeah, it should be.
You think it's on lecture, yeah?
I hope not. If I made that mistake a second time. If they go to my YouTube channel here, let's prove it live. Let's do the stream and a stream. So if I switch to this account, or actually, Wesley James. There I am. I totally picked the wrong one again. I'm 0 for 2 on that. Look, you can see how much the delay is. Oh, it's not that bad. Oh, no. No, it's worse now. Oh. What's it doing?
It's showing you 3. Yeah.
Oh, okay. Sorry. I thought it kept switching tabs. I'm like, I'm not switching tabs. How's it doing that? All right, whatever. I accidentally picked the wrong one again, so sorry for that. Don't even know what happened. Whatever. It's there. It's fine. Okay. But it is working.
Okay. Keith, have a lot of people already submitted the quiz?
I don't know. I have no clue. That's a great question that I don't know the answer to.
I was having issues with question 1. I did the work.
Okay.
I didn't get a right answer, and then when I redid the work on another question again.
Chat with me at the end. If there's a typo, yes, I definitely want to fix it. There's always a chance of that. I have not gotten any emails yet, which is usually a good sign, but doesn't mean that there isn't a typo. And we'll chat about that. So we have half the PowerPoint left. So let's do a quick recap. Just run through this real. Oh, Joe, go. Yeah.
All right. The inventor of the ballet skirt was struggling for a name until she finally put two and two together.
What is a ballet skirt?
You don't have to say two together. No, wait, I just didn't hear it.
Yeah.
The inventor of the ballet skirt was struggling for a name until she finally put two and two together.
I get it.
Yeah. It's good. See, I told you. My wife spent a lot of time curating these jokes. They're good. All right, so we chatted about capacitors last time. The first one was a sliding jar. So cool. Stored charge. You remember the whole point of this is it's useful to have things that store charge. Why? Gave a bunch of examples of things. Really cool. Capacitance definition Q over V. Then we derived it, and we realized it's a geometric quantity. Epsilon naught A over D. And then we did some things. We looked at them. We looked at them charging. Cool simulation. Check it out. Have fun with it. Then we talked about what stays the same. This was kind of the last thing we covered. What stays the same when we're connected to a battery? The voltage, regardless of what you do to the capacitor. If it's the only thing in the circuit, it gets the whole voltage of the battery. Why? Because why does it get voltage in the first place? Because of the battery. What stays the same if I disconnect it and I throw it across the room? Well, there's two answers. What happens if I disconnect it and then change its distance, the charge, because it's stuck on there? It's got nowhere it can go. You could take the two plates, literally split them apart, and then move them infinite miles away. They're still going to have the same charge as long as you didn't discharge them. And then the last, what stayed the same was if I charge it, disconnect it, discharge it, meaning use it for an application where the charge is then flowing through, and then chuck it across the room, capacitance stays the same. And just to show you all again the simulation, just this discharging, charging. I did it. I don't know if I actually showed you all the discharging. So we're going to see this in later classes when we eventually do RC circuits. So if we build our capacitor circuit, and we'll do a really, really basic one. So all of them, you have to have a resistor. I obviously haven't taught you what a resistor is. You're like, what is this colored thing? The beautiful thing about resistor is the name tells you what it does. It resists. It slows down the current. So the reason I do this is it just helps the current go slow enough that we can kind of see it. You're like, whoa, why are the colors changing? We'll learn about that too. All fun things in the future. So right now, all I'm doing is just trying to charge this capacitor. So great, nothing happens because the switch is opened. It doesn't see the two sides of the battery. It doesn't see the high and the low. It only sees one side. When I connect it, it slowly but surely starts filling up with charges. That's what all those little specks are on there. If I zoom in, it's easier to see that, woo, now it's charged. So what? What's the point? The point is I can now, for example, connect this to a light bulb. So I can connect this side. Yeah, that's fine. So now I can disconnect the battery. Normally that'd be done with a switch, but I'm gonna be lazy. And I can now connect this capacitor to something else. So I can have another switch somewhere such that, great, the battery is disconnected. So the battery is no longer doing anything, but the charge is stuck. It's got nowhere to go. The charge, this negative charge, can't get to the positive side. There's no way for it to get there. It's trapped. But if I connect this, now I'm going to have a pathway for it to flow through. And so when I do that, the light bulb, oh, look at it go. It's very hard to see. But if I zoom in, again, I purposely slowed this down for y'all. The charges are very slowly, because this is a very high resistance, moving through and discharging. It's kind of super slow. So I'll make it go a little bit quicker this time. So let's disconnect this one, connect this here. Boom, it charges on up again. This time I'm going to make the resistance way less. So it's going to be super quick, way more exciting. Oh, so cool. All right, disconnect this end, then do this. And look at that go. It's discharging, and it's discharging much quicker. So batteries and capacitors can both be used to power a circuit. We'll learn about that kind of eventually. Batteries provide think of them like your hose. They provide a steady amount of current. They can't provide a lot of current. Your garden hose can't spit out that much water, but it still supplies water at a nice, steady, long rate. A capacitor is like filling a bucket. It won't last as long, but I can dump that bucket and get a lot of charge really quickly. So just two applications of that. If you want a lot of charge really quick, capacitor. If you want a long, drawn-out amount of charge, but not a lot, you just can't supply a bunch at once, battery. And they also do a ton of other things. Capacitors also help with filtering out high frequencies and low frequencies. And that's like, what do you talk about? That's AC circuits. We'll see how much we can get to that. But this is a fun thing to play around with. It lets you see stuff. We're going to be referencing this a lot, this simulation, as we go through circuits. Because when you connect wires, you can't see what's happening. This lets us see what's happening. It lets us see the charges moving, and it's super, super useful. So seeing is believing, right? Some people say that. Whatever. So capacitors, great, constant, jazz. New things. So this is just a reek. So next step, let's find the energy stored in the capacitor. So reminder that the energy stored in a system is Q delta V, where we have to build it. The really, really important thing here is that we're building the charge, or we're building the energy. Every time I add another charge, it increases the energy of the system. So if you're like, what's he talking about? Remember that when we had this whole triangle situation, and I said, what's the energy stored in this 3-charge system? This was when we did a while back. What we did is we found the energy to bring 1 charge in. How much energy is required to bring charge 1 in? And we pretend like the others don't exist. It's 0. Yeah. Then we bring the second charge in, and it sees this first one, and it has to fight its voltage. It has to fight that force. There is energy required. So there's an energy required to bring the second charge in. And we said that that was KQ. In this case, like if we said this is A, KQ over A. Now if I bring a third charge in, I now am fighting both of these charges. So that's the energy required to bring the third one in. So it fights charge 1. It then fights, and this needs to be KQ squared. It fights one of the charges, it fights the other charge, and so the energy required to bring this second charge in, or this third charge in, is 2 KQ over A squared. And then the total energy was all of these added together. The energy to build the system. This concept of the energy building, like each one takes more and more energy, but you add all of them together. This is really important for us to derive the energy stored in a capacitor. Because what are we doing in a capacitor? We bring 1 charge in, then another, then another, then another. And we bring not an infinite amount, but an infinite amount of these small charges until we have all the charge. So we're going to integrate. What is the same thing as doing an infinite sum? An integral. We keep using these integrals for these infinite sums. So we want to find the total energy. So for example, this actually might be better to represent like this. If we want to find the sum of all the energy changes, we're going to do an integral. And so, I want you all to do this integral. And you're like, what? It's really easy. Check out the bottom. For a capacitor, C equals Q over V. This integral says that if I want the total energy, of the system, I'm going to do the integral of V dq. Just swap in, solve for V, that bottom equation, solve for V, plug that in, and then integrate. Try it. You can do this. If it helps, you can kind of call this little q if you really want. So you need to make the substitution and you need to set your bounds of your integral. What am I integrating from and to? Zero Q. Oh. Yeah. We're just integrating. We're adding this charge. Oh, yeah. Yeah. That's the integral just over here. 0. Yeah, but you can't get this without the integral. Right. Nice. Okay. So what do we? Yeah. We'll just call it capital Q. Okay. Yeah, total charge. And then we just make the swap in. Yep. Yeah. Solve for V and then swap that in. Thank you. Yeah. Perfect. And you just integrate that. And to clarify, this Q is Q.
I said 0 to full charge.
Easy integral. So what are we integrating? What variable? How much charge do I start with? How much charge do I end with? There's a cap. Take a letter for it, basically. I tend to use cap. What's called the total charge, capital Q. Yeah. Until it's fully charged. Yes. Yes. Yep. And that's the whole idea. We start a capacitor with no charge on it, and then we fully charge it. Yep. To some hypothetical charge Q. Yeah. Perfect. Let's Fuji.
Is it capital Q or lowercase q?
So this is all kind of subjective. So I replaced, just to make things a little easier to understand, I replaced the capacitors with a lowercase q, but our bounds will be from 0 to some hypothetical total charge. We like to use big Q for that total charge.
Okay.
What decides the total charge of the capacitor?
That's a great question.
Capacitance times voltage?
Yeah, exactly.
Go back and
You can now, that we're actually going to write this 3 ways, you can now do C equals Q over V and supplement and make this equation 3 different ways. The energy stored. So that is the expression, and then you can sub stuff in to get 3 different forms of it. Yeah. And we're now one thing I did show you is so just gonna stay here.
That's like finding that balance. I feel like it's really hard.
Like literally right before class,
Alright, who wants to derive this?
Really?
Who wants to do it?
is it down?
Yep. Yeah, and I went ahead and put C equals lowercase q over V just to keep.
Or lowercase q. Right.
All right, let's talk about this problem. Okay. The question asks us to find the energy stored on the capacitor, and we've got our equation. Delta U total equals the integral of V dq. And we also have that C equals Q over V. So, using my friend algebra, I can just rewrite that as V is Q over C. And so plugging that into my integral, and hopefully I remember how to do integral still. That's Q squared over 2C, and you got to plug in your bounds. So I forgot to write those earlier. In this case, since we're just going from 0 to some total charge, I'm calling that capital Q. And then I can plug that in, get Q squared over 2C minus 0 squared over 2C. Ta-da!
And it's great. That's the equation for the energy stored in a capacitor. Now, something that's really interesting about this equation. So, yeah, what's the energy stored? It's what we just did. Just to write it again on this slide, the total energy stored in a capacitor is capital Q squared over 2C. Now, through the magic of substitution, we can do this. C equals Q over V. We can shove that right down here. So you can now write this in terms. So we get Q squared over 2 Q over V. The Q's cancel. 1 Q cancels, 1 Q cancels. So you get 1/2 Q times V. And then you can write it one more way. If you then substitute Q equals CV, and you make that substitution in here instead, you get CV squared over 2C CV squared over 2C. I feel like I'm missing something. That should be squared as well. One of the C's cancels, and so you get 1/2 CV squared. So there's 3 ways to get the energy, and it's just from doing some algebra. It's nothing crazy. But what I want to point out to y'all, here's the mistake that tons of people make. The mistake is they go to the formula sheet. Ta-da, formula sheet. They scroll on down. They say, I want the energy in a capacitor. And they use this, Q times V. But then if you look over here, this says the energy is 1/2 Q times V. Oh, which is the right one? This one's for a capacitor, the 1/2 Q times V. This one over here is the general for a point charge. It seems like a tiny difference. But if I ask you on the test, hey, here's a capacitor with some capacitance and some voltage. If you don't put this 1/2 value, you're not going to get the right answer. And that 1/2 value comes from doing the integral. It's not made up. It's not out of thin air. It's because we had to add charge, add charge, add charge, add charge. And after doing all that, you get this 1/2 term, just like you just derived. It didn't come out of thin air. So be very careful. The energy stored in a capacitor, here's all 3 versions, is 1/2 Q times V, is 1/2 QV squared, is 1/2 Q squared over C. All of them are valid except for the one that I wrote wrong. But what's very important is this 1/2 term. I can almost get you. I say you. It is very easy and very common for people to forget this 1/2. You're like, it's not a big deal. It's just 1/2. Well, $500,000 is $500,000. Like, that's not the same as $1 million. Half of something is way different than the full something. And yeah, here's a car, and they give you half a car. That's not a car. Like, look, it sounds stupid, but these things matter. These little things that in math look like, oh, it's just a negative sign. Oh, it's just a 1/2. It's just a small little thing. Yeah, try explaining that to someone when the rocket blows up. And you say, I just forgot the 1/2. I just forgot the negative sign. Like, you got to be careful. You are in a world of precision where a tiny change can result in a massive difference. Numbers, a calculator is going to do exactly what you type in. It won't be the calculator's fault. Can't blame that. So be careful. If I asked a question like this on a test, hey, what's the energy stored in a capacitor? You best believe one of the answers is going to be solved without the half. Because I need to make sure you're doing the right equation. If you just picked one of them, you're not actually using the right equation. You're just picking the one, like, they mean different things. That is a physics mistake, not a math mistake. You chose the wrong equation. So, all right. Now we get to something interesting that's going to be tricky to explain, but I'll do my best. So I told you all way back in the beginning of this PowerPoint, that when we have this capacitor, there's not just empty space in between it. Like real world capacitors have something between them. It's not a vacuum. And there's 2 reasons for that. One is we don't want the charge getting to the other side. We need a barrier. We need an insulator in between to keep it from going across. If we just had vacuum there, they would naturally want to smash together. You can't just like take the air out of it. It's really hard to keep a vacuum there. So that's like just logistically very hard. But it's also worse. So 1, we need it to keep a barrier, but 2, it actually lets you store more charge. And this is where I'm going to do my best to explain to you why it lets you store more charge. And we'll see how it lands. It's not a huge deal if you don't understand the concept about why, but it is cool if you do. So here's the situation. We got 2 different capacitors here. The one on the left, no insulator. The one on the right, insulator. So this harkens back to the beginning of the class where I told you, if you bring a charged, so like if we bring these negative charges here, in an insulator, they're going to push away the negatives. They're going to cause a dipole inside the insulator. So if you're like, what is he talking about? Remember way back when you bring a negative charge near the wall, it pushes away the negatives, resulting in this kind of attraction. This is the whole induced dipole. It's why water is such a good solvent. It dissolves things because of that. It induces dipoles. So why does this matter? So we have our original electric field here. In this new situation, we have our original electric field. I'll draw it here as E0 from the positive terminal to the negative. But what we also have inside is another electric field pointed the other way. We call this the induced electric field. Why did that one occur? If we zoom in on this, there's these charts. Remember, we induced this dipole, so it makes another electric field. Why does that all matter? It makes the net field smaller. Why is that good for us? That means we can cram more charges on there. We can cram more charges on there now because these capacitors are limited by the electric field that they can kind of make inside. It's based on voltage. If you all also remember that V equals E times D. And I told you all that the voltage was determined by the battery. So if this voltage is a constant and this distance is a constant, if I kind of make this electric field will therefore also be a constant. Regardless if I put that insulator in there, it wants to have a field of a certain strength. So by putting this induced field here, I can make the field from the capacitor bigger, such that the end result is the same size. So let's call this E total. E total is going to be the same size here. How do I make E total the same size? By putting more charge. Let's call this E due to the capacitor. Whatever, that's kind of overgeneralization. So there's a few ways to kind of word this. You're able to add more charges to get the field such that it's still the same. Another one is you can think of these charges inside as like masking the charges on the other side, so I can cram more charges on there. The end result is the same. When you put a insulator inside of a capacitor, you can put more charges on the capacitor. That is the end result of this explanation I've tried to give. If you put an insulator in a capacitor, you can now cram more charges on those plates because there's this insulator inside that's kind of masking things and reducing your field. So again, here's kind of the same logic I just wrote down. The net field is a constant. So therefore, I can have a larger electric field. How do I get a larger field? I have more charge. End result is that capacitance goes up. That's the end result here. In this, my E naught, my electric field made by this, goes up. And if this goes up, reminder that this equals sigma over epsilon naught. That means my charge goes up. My charge goes up, my capacitance goes up. That's the definition of capacitance. Long-winded thing that says an insulator is good. Makes your capacitors better. Not only is it a requirement to actually build these capacitors, it actually improves things. Mathematically, how does this all pan out? You get this thing called the dielectric constant. It's dependent upon the material that you put in it. The higher the dielectric constant, the higher your capacitance. It literally just takes your original capacitance, and when you put this dielectric in there, it then increases it by a multiple of that. So if you decide to put, so vacuum has a dielectric constant of 1 because it doesn't improve anything. You put some Teflon, you've made a capacitor that's twice as big, twice as high of a capacitance. You put some paper, it's 3.7 times bigger. You put some titanium dioxide, whatever, it's titanium with oxygens, it's 110 times bigger. So it's a way to basically get more bang for your buck. It's just by putting something in between it. It's nice. And it increases the capacitance. Interesting enough, it decreases the energy stored. And that's a little bit kind of funkier to explain. I mean, mathematically, you just swap it in for C, and you can kind of see that it's on the bottom. If I take this new capacitance and I put it on the bottom, that's on the bottom. The other reason is that the insulator is kind of holding some of those charges there, so you're not storing as much energy from that. They're trapped there due to different mechanisms, whatever. It doesn't really matter too much. At the end of the day, we care about being able to hold a bunch of charge on it. That's like the benefit for us. But it's kind of interesting that it's less energy, which is kind of weird. But it's more charge on it, which is useful. At the end of the day, when we then discharge it, we can get all those charges to do cool things for us. All right. Something I also want to point out here, I've mentioned this a few times. So this permittivity down here, that's that 8.854 times 10 to the minus 11. 12. You've been using this probably in some problems. When you're in different materials, you get this different permittivity. This is very relevant for electrical engineers. This is very relevant for physicists to know this permittivity. Permittivity, hand-wavy defined, is how easy or difficult it is to make an electric field in something. And this is larger in other materials. It is more difficult to make an electric field in like any material than a vacuum. Vacuum, there's nothing there. Other things, there is stuff there. So, great. There's this thing. Cool? All right, let's do a problem on capacitors. It's got everything in it. It's a parallel plate capacitor. It has an area of 200 centimeters squared. It's separated by 4 centimeter air-filled gap. If it's connected to a 500 volt source, what's the charge on it? What's the energy stored on it? What's the electric field? And then the last one is if I put a liquid with a dielectric constant of 2.6, how much additional charge will go onto the plates? Try it out. Y'all got all the equations. This one is very straightforward. What am I solving for? What equations can get me that? What do I have? All that good stuff. That's a great point. I'm missing that. Oh, so sad. All right. Yeah, I should put that there. All right. I'm going to shift everything. Part A is what is the capacitance? If you're like, why is that? The unit here is in picofarads, which is the unit for capacitance. So I'm just going to shift everything. There is no part E. So everything's going to get just shifted. So find the capacitance, find the charge, find the energy, find the electric field. Find how much extra charge if you put this nice dielectric in there. I hope you all yearn for, man, if only this was all just in variables. Numbers stink. I'm convinced you that that's good. Yeah, it's one of the places. That's a good question. Yeah, it's there in one of the places in the same area. Yeah, good question. We kind of already counted for twice the area because when we found the electric field, we doubled the fields and that actually doubled the areas.
Yeah, I mean that makes sense.
Yeah.
That's one way of doing it. Or if you're looking for epsilon or sigma, or sigma over epsilon. So you know the charge density.
Two ways get you the exact same thing. Which, because I asked you for the charge, you can easily. Yeah. But you get the same answer, and whoa, it all works. Negative 12.
E to the 12?
Yeah, Negative 12.
Coulomb squared over Newton squared. It goes to the minus 12. Did you convert your units to meters? Oh, yeah, you are going to have to. No. That only works if the units all cancel out, but I got centimeters squared, I got centimeters, so one of them will cancel.
Tricking us, are we?
No, it's not tricking. It's life. Yeah, gotta convert your units. That's gonna be. But see, look, numbers suck, don't they? If I didn't give you if I just told you an area A and a distance D, you wouldn't have to deal with the suffering. The units won't count. One's squared, one's not. Well, that's not tricking. It's like so important. You gotta be in base units. Variable form is so much better. You wouldn't have to do this if I just gave you an area A. The distance D. So much nicer. Gotta do it one square, one not. If you didn't convert your units, you should have. That's probably the most common thing I'm seeing. It's centimeters squared and centimeters. You got to convert to meters. They don't just cancel out. You need to convert to meters. Base units never goes away. If you don't know when they're going to cancel, then make sure you just convert them. Minus 12. Minus 12. Yeah. That'll give you your two capacitors. Right, and then same voltage. I'm plugging in. So that's going to give you the new charge. This says how much additional charge.
Oh, so it's just a
subtle.
difference.
It's a subtle.
Oh,
yeah,
clever.
Yeah, it's subtle. Yeah. I wouldn't try to be this mean. So like on a test, I probably wouldn't do both.
Right.
If I gave this, I wouldn't have an answer that was that charge.
Yeah. I see what you're saying.
I wouldn't be that
Makes
mean.
you read carefully.
I never want to do this problem because it's like they misread.
One small thing. Yes.
For the first part, minus 12. Yeah, your magnitude is off the other way. So when you're still right now
What's that?
okay, so
Well, you don't have to do 200 squared.
And make sure you convert to meters.
Oh, because we keep it.
Because when you are converting units,
Yes, I see. Because then you get meter squared and then you get centimeter squared. I 1 meter.
1 centimeter squared is. Wait, meter? Yeah. Okay. I should 1 centimeter squared is 1.
I converted it wrong.
Oh, the doubling down on it?
Yeah.
Yeah. Yeah, the easy way to convince people of that is 1 centimeter squared is this big. You try to tell me that it's point. You can think of the consequence of it as 0.1 meter squared or something. Wouldn't make sense.
So it's gonna be 0.02.
Minus
What did you get?
Yeah, 0.02 meters squared.
Yo, guys, meters
Those are all the
squared,
U
centimeters
equals like
squared,
1
not
half
1 over 100
equation. So 1 half QB is 1.
Oh, it is a 1 over 100. Yeah.
So that's going to give you like another that one is
No, radius is
No. It should be negative 12.
Yeah. Okay.
That looks
Yeah.
No, that's fine.
The last one, I think I had a different answer. I'm not sure. For the dielectric. It's like when I calculated it, I get it's just so it's 2.6, right? Just times the old capacitance, which was that.
No, yeah.
And then I can just multiply that by. Oh yeah, sorry.
No,
I'm
it's
all old
fine.
school.
No, the E is so good because then you don't have to. If you square
Yeah, I don't
it,
even know where the E is on
it's
here.
right there.
Oh,
It's better
nice.
because if you square things,
Yeah.
you don't have
yeah.
to put parentheses.
Oh, that's
And when you
nice,
divide,
actually.
you also don't have to put
I'm
parentheses.
gonna have to start there. It's gonna be a hard habit to break, but
So then you just take that, multiply it by
voltage, right?
just by this.
Oh, wait, well, I already did that. For the, this is my new
Oh,
charge.
okay,
This is
yeah,
my
yeah.
new capacitance,
So
right?
the capacitance.
And then for the charge, I can just multiply
So you just
by the
multiply that by
voltage.
500.
Oops.
Okay, cool. And then you should subtract the original voltage, 22.
The original charge.
22 E, yeah, 22 E minus 9.
Okay, now it's working.
Yay!
Oh, that was good before. Thank you.
No, I'm glad it works.
Yeah.
Boy, this one I think I got from a book that does something. All right, so parts A and B are up here. I'll start working on parts C and D if you haven't gotten to those yet. But it is just very much, hey, what am I solving for? What equations have those things? Chuck them in. This is some of the most straightforward kind of problem. No tricks other than converting your units. So yeah, if you're keep working on it, just know that I'm gonna start like I'll just like have it up here and just go through the equations and things like that.
squared is 4E.
The first one you did was just find the charge. That's the charge on the capacitor. This is directing the entire Oh yeah, it was a typo because the first one A should be finding the capacitor, B is the charge, and C is the charge. Okay. And you'll use like
Part A,
the
it's excessive with the charge on it.
Yeah, it was like A is now.
yeah, he fixed it up there. About
Part A was the, yeah, if you look at the answers, I realized that, well, Tyler realized the first answer is farads, that's capacitance.
Yeah.
So everything just got shifted.
Yeah.
Yep, yep.
I kept getting an E wrong, and I thought you were doing the conductor, but I was right, so 11.5. For part E?
Yeah.
That's the,
Oh, part E. I thought you meant
Oh,
E,
no,
like.
no. Yeah, I didn't even do it the other way. I just did it like this, but
I mean, you should get this.
you get this because you can just do the sigma over epsilon. Sigma would just be the charge over the area.
All right, so in case, just to kind of walk you through these with words, the first one, it says for capacitance, you got two equations. One of them you can do, one of them you can't. How do you choose what equation? Which one can you actually do? The first one says epsilon naught A over D. Hey, I got area, I got distance, I got epsilon naught, easy. The second one says C equals Q over V. I have voltage in this problem, I don't have Q. So, can't use that one. So use the one you can. And you plug the numbers in, you get that 44 picofarad. Part B says find the charge. What's the equation for charge? Well, there's a bunch, like you look through the formula sheet. Hey, this one has capacitance and voltage. I have capacitance and voltage. Rearrange, solve, you get 22 nanocoulombs. A lot of this comes down to how do you know what equation to use? It's very much, what am I solving for and what do I have? Like, unfortunately, that's just kind of what it boils down to. So when you're trying to build something at home, you're like, what? I want to build something. I want to make a workbench. All right, what do I have? You use what you have. If you don't have screws, don't use a drill. So it sounds stupid, but the more familiar you get with your tools, the easier it is to choose the right tool. The easier it is to choose which one, because you kind of have that in mind. All right, part C, I want the energy. There's the three different equations. You could have used any of them because we have capacitance, we have charge, we have voltage. So I just picked the 1/2 Q times V. You very well could have picked 1/2 Q squared over C. I think that's one. Or 1/2 CV squared, whatever. It doesn't matter. You get the same answer one way or the other, 5.5 microjoules. You want the electric field. You got two options. We got two options for electric field. Either the definition of electric field in a capacitor, sigma over epsilon naught, which is Q over A epsilon naught. Or the change in voltage in a capacitor is E times D. Normally the change in voltage is an integral, but because a capacitor has a constant voltage, we can pull out that E, and it's just E times D, and yada, yada, yada. And you get 125,000 newtons per coulomb. The last one is got a little trick to it, but the trick is really obvious once you know what you're actually solving for. Part E does not say how much charge can I store on it. It says how much additional charge can I store on it. So part E says Q extra equals question mark. So I put a dielectric in it, and that's going to increase how much charge I can store on it. How is it going to increase that? Well, based on the slide I just showed you, remember that the capacitance is different now. By putting a dielectric, I have changed my capacitance. Why is that significant? Well, my new capacitance is going to be my dielectric times my old capacitance. So it's just going to be 2.6 times my original capacitance. Why does this matter? If I get my new capacitance, which is something, Tyler, do you remember what it was? I have to get on my calculator, otherwise it's devastating. I hope you all are appreciating problems that don't have numbers now. Like, gosh, if we didn't have to work with numbers, this problem would be so simple. If you wanted to find the capacitance, the answer would literally be epsilon naught A over D, and you'd be done. If I then said, what's the charge, you would just take that. Oh, it's so much better without numbers. Numbers are gross. Does anyone have that, or maybe Tyler? Who's got the capacitance, new capacitance? 2.6 times 44e minus 12. Should be like 100-ish.
1.15 times 10 to the minus 10.
1.15 times 10 to the minus 10. So what? Now I can find my charge. How do I do that? The same way you did it in part B. How do I find my new charge? C times V. 1.15 times 10 to the minus 10 times my voltage. It's the same voltage. And I'm just going to put this on another slide because I'm running out of space. Actually, yeah. I'm just going to squish everything. Wow, so much space now. All right. Someone tell me what that equals. 1.15 times 10 to the minus 10 times 500.
5.76 times 10 to the minus 8.
This is not the answer. This is not the answer. Why? This problem didn't say how much charge. It said how much extra. So I'll give you all some time if you haven't tried it. What do I do with this? Think about it. Try it. See if y'all can figure out how do I get what I'm actually solving for. How much additional charge can this store? Think of the wording and what that means and all that good stuff. So that is the charge on the new capacitor.
Yeah.
So using that, how can I find how much additional charge? All right, so hopefully you realize that Q extra is my new Q minus my old Q. So the definition of how much extra. How much now do I have? How much did I have before? Subtract the 2. And you just subtract 5.76 e to the minus 8 minus 22 e to the minus 9. That's from up here in the top right. We did that before. And you get that 35, I think. 36, 30-something. 35 e to the minus 9. So on a test, I'm not going to be mean and do something like that where it's like really subtle. If I did ask something like this, like how much additional, one of the answers wouldn't be the 5.76. I don't want you all to miss a problem because you miss the understanding of like what it's asking for in that way. But yeah, this pretty much covers the gambit of capacitor problems. You've done you got the field, the energy, the dielectric kind of put in there. It's all there. So this is a good problem. It's pretty basic. There's nothing complex going on here. We're not doing anything crazy. There's no integrals. But each of these types of problems, there will be problems like this sprinkled in on the test, just to give you all some maybe peace of mind. The test isn't going to be all crazy problems. In fact, a lot of it is going to be basic kind of, can you do the basic calculations? And then there'll be some mixed in with integrals and some mixed in a few steps and, some conceptual ones that have no math whatsoever. But this is just, can you use the equations? No fuss, no muss. And if you can at least do this, you should probably get at least a C in the class, I guess. Yeah, because this is like the basics. If you can only do this, this is fine, but this is only going to get you kind of to a C. If you can't do any of the integrals, if you can't do any of the multi-step problems. And I understand if right now this doesn't make sense, but hopefully after you all practice this some, this should be one of the easier problems for you all. That's the end goal. This should be an easy type of problem for you all. Maybe not right now, but after you've reviewed the stuff and spent some time on it. All right, there's a nice blank slide. Okay, so what are some applications of this? You don't need to know this, but this is fun and interesting. Stud finders, those are the things that you put on the wall to find where the wooden studs are. If you're not familiar with what a wooden stud is, behind drywall is your wooden structural beams in a wood-framed house. Pro tip, if you want to hang something heavy, put it on a stud. Otherwise, it will fall. Always. Unless it's like a picture frame or something light. Whatever. How does a stud finder work? It's just a capacitor. So in this thing are some plates. And now granted, this is where we get to these fringe effects where basically the electric field actually does this curve. So yes, it makes parallel lines in between them, but it also kind of curves outward. So why does this matter when there's a stud behind it? So this is when there's a stud. This is when there's no stud. When this stud is actually acting as an insulator kind of in between them, kind of sort of. And so it changes its capacitance. It increases the measured capacitance between these plates. And that's how it detects when there's a stud. It's just moving around. It's constantly measuring its capacitance. When its capacitance changes, it says, oh, something changed. There's a stud there. There's something solid, whereas otherwise there's just empty air. So that's how stud finder works. Your phone's touchscreens also are a similar kind of mechanism, where when your fingers go around it, your fingers are acting as an insulator, and there's a bunch of sensors behind here detecting the capacitance all across your screen. There's a bajillion capacitors almost, you can almost imagine. And so your finger moves around, it changes the capacitance of each of these based on its location, and boom, that's a touchscreen. So capacitors, they're also used as sensing devices, super useful. All right, nice little summary slide. It's all the things. I kind of summarized a lot of this before. Yay. Good to look through, but I won't spend the time on it now. All right, we are on the last thing I need to teach you all, series and parallel. It's going to be some rules. Series is going to be series is going to be easy. You are going to have no problem spotting a series circuit. A parallel circuit is going to, I hope I can teach you all how to do it well. We'll see how that goes. But I'm optimistic. So, series. I always think of the World Series game because it's got the word series in it. Series means one after another with no alternative paths in between. One after another. You cannot go another direction. You have to go through each element if they're in series with each other. There is no alternatives. World Series game, each game is one after the other. There's no alternative game split in between them. So this picture, which I like, shows a series circuit. It shows two circuit elements and a battery. If you're like, what the heck's going on here? We have a battery, which increases the voltage, has a high voltage on one end, has a low voltage on the other. What does the battery do? It lifts up those charges. Remember, it's like adding, it's almost like a ski lift. It's taking that voltage and lifting it up through a chemical reaction. And then we think of this water like the charges. The water flows around. Notice it's the same height here. Wires don't change the voltage. And then it hits some circuit element and it drops some. And then it hits another circuit element and it drops some more. And so something nice here is if the total voltage is here, this is just good foreshadowing. If this one drops by V1 and this one drops by V2, what's the relationship between V1, V2, and V total based on this picture. You can see it visually. What do I do with those V, like, what's the relationship? Who's feeling confident? You add them. So this is a nice visualization to show you that when you have a circuit in series, the voltages add up to give you the total voltage. This is something we're going to need. The change in voltage across the first element plus the change in voltage across the second equals the total voltage. This is specifically true in series. Only in series is this true. Also, how does the flow of water compare to this circuit? So say I have a certain flow up here. How is that flow going to compare through here? Is it going to be the same? Is it going to be different? In fact, I'm going to make this a clicker question because I think it's interesting. How does the flow of water through the top paddle wheel compare to the flow of water through the second paddle wheel? And you're like, what's there's two paddle wheels here. One's on top, one's on bottom. And it seems simple. Remember, all learning is done by connecting things you understand. So if you all can understand this flow of water, we can understand the flow of charge. And that's going to be super useful. So it's either higher, lower, or the same. That's the only three options. What do y'all think? I'm a little paranoid. Okay, cool. I'm not asking how, so let me clarify this. I'm not saying how fast does the water go. I'm saying the amount of water per unit time. The amount of water per unit time. That's why I didn't say how does the speed. I said how does the flow, flow rate. Flow rate is how much water per time that passes through something. So how does the amount of water that goes to the top one compared to the amount of water that goes to the second one in the same amount of time? That's what I'm asking.
So this one gets one was higher than the other. Really extra water. Say the top was higher.
That's the whole goal here is to help them understand.
I like it.
I wish I had this class for you.
I've spent a lot of time thinking about how to convey this idea.
I think it's
The first one was slower. That would mean less water reaching the bottom. It'd also be slow as well. Like, and if the first one was faster, the second one was slower, that would mean more water's getting there, so this one can't process it as quickly. So what would happen? It starts to, but that's not going to happen. It can't. So if more happens, it's still just going to push through the other one, however it can. This gets the idea that fluid is an incompressible thing. So even if one part wants to be faster, it's too bad. Like, you ain't got anywhere to go. You got to just push through. Yeah. This is also why a wide river gets faster when it gets narrower. A lot of water gets through a narrower. Area gets less, but the velocity gets higher. The flow rate is the same. This is only true in series when there's no alternative. If I have alternative paths, I'm going to pick the easier path. If it wasn't, say like way more water. Overflow is fine. It can go anywhere that Joe traps. This is the river It might even make faster like so it goes faster. So the same amount of water is flowing through it. The area got less All right, give y'all 10 more seconds on this. All right, in 5, 4, 3, 2, 1. All right, so I know this is water, which you're like, why are we learning about water? Because if you can understand water, which you do, you can understand electricity. So I'm going to tell you all the answers. So what happens when a river is really, I'm going to use a different analogy. When a river is really wide and it gets really narrow, what happens to the speed of the water? It gets faster. Why? Fluids are incompressible, meaning that they can't get closer together. So you need the same amount of water flowing through it. The other thing I tell people is if we imagine that this first one was faster, but this second one couldn't go as fast, couldn't like quote unquote process it as quickly, you're going to get a buildup. But where's it going to go? There's nowhere for it to go. So long story short, the flow is the same everywhere in this entire circuit. Everywhere in this circuit, the flow is the same. If some parts are more difficult, that's just going to slow everything. Because otherwise, you're just going to build up. Like you can't just, it's got nowhere to go. Think of a traffic jam. Eventually, when the cars in front of you stop, guess what happens to you? You stop. Like, where are you going to go? Assuming that there's no side roads, assuming there's no alternative paths that are easier. This is going to help us like prepare for that. This flow of water is the same. If you understand this, it's the same principle for current. So when we start learning about current, that's going to be true as well. Current is the flow of charges, and they follow the same rules that water does. So that's going to help. That's going to hopefully help that out. Ooh, good job. All right, cool. So I have this situation. You're like, what? This looks weird. Maybe it doesn't to you all, but I also want to challenge you on showing you circuits in ways that also might confuse people. So I got two capacitors here. On one end is a high voltage, and on one end is a zero voltage. This picture, so this is what the symbol for a capacitor is, by the way. Hopefully that wasn't like surprising to you. It's two infinite plates. It looks like a capacitor. That's why we draw them like that. In the US, sometimes they'll do this to denote which one's the positive and which one's the negative. Not that it matters at all. Whatever. So this circuit here says I have a high voltage to start with, and you're not going to see this word ground. You'll just see this symbol. This symbol represents zero voltage. So this is a really common way of drawing circuits. This circuit is the exact same thing as this. Boom. So this is traditionally how circuits are often drawn in physics classes, and it's the exact same thing. That symbol at the top is a battery. So I'm teaching you all some symbols here. And let's say this is a 5-volt battery. What does a 5-volt battery mean? It means one end is 5 volts, the other end is 0. It's the same. These two pictures are the same thing. And the reason I'm showing you both is it's very common in physics classes to draw everything with these batteries. But when you all do if you all do any actually electrical diagrams, this is far more common. And I didn't see this till much later, and I didn't know why. It's the same thing. So that's why I want to show you all this way of doing it. Okay. So my question to you all is I got two capacitors. The first one gets charged up with some positive charge on the left and some negative charge on the left. And my question to you all to think about is, wait a second, where did that one get its negative charge from? Spend some time, think about it. This one you could be like, oh, it got it from the positive thing. It's connected to that. But this one, what? Where did it get it from? Think about it. This is going to be very important for us deriving this. It's going to help us understand something. Where did that negative charge come from on the first capacitor? What's the only thing connected to it? It's from the other capacitor. So if I steal a negative Q from that one, what charge will that plus side turn into? Positive Q, and then that subsequently makes it. That's proving that charge is the same.
Oh, okay. Alright, let's say, where did you say that you Right, and if you think about the flow analogy, it's still constantly flowing through, the only way to keep going through is if you have a plate with a star. And just like a battery, it all flows from a high voltage to completing like a loop. When it goes to ground, it can be a little confusing because there's a lot of times a battery with a wire on both ends. You can actually see it, but it's still complicated. Yeah, slowing.
All right, so hopefully you've been able to think about it. Went around, and I'm sure many people are going to say it gets it from the ground. But here's the problem. Sure, so the ground, and this is also a fun fact for you all. Why is it called the ground? Because it often is literally a wire plugged into the ground. I'm like, that's not an exaggeration. Like almost every building literally has a copper wire just shoved into the ground. Look like the dirt outside. Why? Because the earth is like an infinite storage of charge. The earth is like super big that you can like get as much charge as you want from it or add charge to it and nothing changes because it's massive. So it acts as a source of zero voltage. You add charge to it. You add a drop of water to the ocean, you're not going to notice its voltage increase, its height increase very much. You take a cup of water out of the ocean, its height's not going to really change much. So that's why this is called the ground. All right, but you're like, it's coming from the ground, but what? They can't jump. How are they going to get across there? That's an insulator. There's a gap. They can't jump that gap. So the negative charges can't come from the ground. They can't jump that gap. That's the whole point of an insulator. So what's this connected to? This plate. And if I steal a bunch of negative charges from that plate, specifically Q, what's it going to turn that other plate to? What charge? It's going to turn it to positive Q. And if this one's positive Q, now that's going to attract charges from the ground, specifically negative Q. And I've proven to you all that charge in series is constant. That if you have a bunch of capacitors connected in series, they all get the same charge because of this. Ta-da! So capacitors connected in series with each other have the same charge on them. And what's convenient is we can then like combine these capacitors together into one capacitor. This is going to be super useful, and then we'll do some problems eventually with this. I might punt them to Tuesday. For today, I might just emphasize series and parallel, and then we'll actually do the math problem on like Tuesday or something with it. But yeah, I mean, it's pretty easy to see what we're going to do here. If you're like, what do you mean it's pretty easy? If I just like get rid of this middle, it kind of looks like one capacitor. But this is super, super useful because, and I told you all this before, when you have one capacitor in connection with a battery, it gets the voltage of the battery. When you have one capacitor connected to a battery, it gets the voltage of the battery. And then you can do stuff with that. And we'll do stuff with that eventually. So how do I combine these capacitors? All right, we've used some logic here. So I already mentioned this to you. This one gets a voltage drop. This one gets a voltage drop. We already answered this with the water wheel thing. What should those voltage drops add together to in this picture? 5, the total. I go from 5 to 0. How do I get there? I drop a little, then I drop a little, and boom, that's 0. So the total voltage drop equals the voltage drop of 1 plus the voltage drop of 2. If you had 10 of them, you just keep adding them. Now, we're going to use this equation, C equals Q over V. I want you all to try this out for yourself. Solve for V, and then swap it in there, and then cancel out what's the same everywhere in the equation. So take this, solve for V, take C equals Q over V, solve for V, and then you can label it like totals, and then put it in that equation on the left. And a variable will be the same across all of them. And you can see in our picture what variable is going to be the same. See if you all can derive how to add capacitors in series. You derive the expression. It seems small, but it's a cool thing. Yeah, it's looking good. Let's do the same on this side as well. And get rid of the, you won't need the triangles anymore either. We just use the triangles for voltage the rest of all this. Alright, so rearrange this to solve the V. So V equals. Boom. Yep. Now take that and swap it. Yep. Instead of total, V total, put Q total over. So it's the same pattern. So that's actually what we're trying to solve for here. Oh, for each one. Each one's gonna, yeah, when we combine it, it's gonna have its own total resistance. What about the charge overall? What do we learn about the charge in series? So in series, we have so what we want to do here is then write this one also as Q and said so this will be C1, this will be C2, and this will be C2. So what we're trying to do here is we're trying to have how do we add these capacitors together to turn into one capacitor? Which for now you just have to trust me is super useful. Then eventually you get the battery that's going to be useful for us. We'll see when we actually solve some problems with it. Alright, Tyler, you want to do this one?
Like this?
Just C1, C2.
For each capacitor.
Yeah, and even V total.
Okay.
This one also will be Q over C.
Oh, gotcha.
And we just label which C. So we have, and you can even label like
So Q total.
Yep.
capacitance?
Yep. And you can
And
even
the
put
Q
Q
is
total, Q1, like you can first show that.
Okay.
And
you
then
can
see
get rid of all the
all
Q's.
the same.
Right. So then it's just the 1 over.
Yay, and ta-da, we derived it. Exciting. No, you're good to go. Yeah, go for it.
Alrighty. So for this one, the first thing we're going to want to do is solve for the V. So we can see from Q over V that we can rearrange this and get V by itself. So it's going to be the charge divided by the capacitance. And you can see here that we'll call this, instead of the total voltage, we will make it 2. We'll say Q, what, total?
Yeah.
Over the capacitance, total, is equal to, we'll say Q1 over C1, the first capacitor here, plus Q2 over C2, that second capacitor here, except that all the charges on here are the same, so we can just get rid of all of them. And we'll say that the total capacitance here is equal to 1 over the first capacitor plus 1 over the second capacitance.
Ta-da!
Yep. And there you go.
And this is how we can turn 2 capacitors into 1 capacitor. So the next slide's a nice, pretty little, well, it's a little nicer there. So when you add them in series, you get this 1 over C1 plus 1 over C2. And so the whole point here is that I can take a bunch of capacitors in series with each other, and I can turn this into effectively one capacitor. And it's much nicer to work with this 1 capacitor when we start doing, for now, trust me that it's useful. And then I'll show you later on why it's useful when we actually solve some problems with it. To turn these 3 into 1. I mean, you can hopefully imagine that one thing is easier to work with than 3 things. Like that's the thought process. So yeah, that's how you add them in series. It looks kind of funky, this inverse thing, but we derived it together. Yay. All right, and normally I would do a break at this point, but we are right at the end. We're just going to do parallel, and then we'll be done for today. So we're going to do parallel, and then that's it. We're not going to actually solve any problems with it. Like we're not going to do the last problem, that we'll save that for next time. All right, so parallel. It's another picture with this height thing. And here's something very, 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 very important. Parallel doesn't mean that the elements are literally parallel to each other. That's what people fall in the bad habit of. They're like, oh, they have to be parallel to each other. No. You're going to see what I mean on the next slide where I give you some crazy circuit diagrams. Parallel means they start at the same voltage and they end at the same voltage. So look at this picture. These are in parallel, not because they're literally parallel to each other. They are in parallel because the height on one side is the same and the height on the other side is the same. That's the technique you all need to know. Just because the path splits doesn't mean my height changes. In fact, if the path splits, my height does not change. It stays the same. You can see that in this picture. On the top, the path splits, but my height, my voltage stays the same. On the bottom, the path splits, but my height, my voltage stays the same. This is very important because if you fall into the habit of only being able to identify when they're parallel, and I give you a question on the test that they're not literally physically parallel to each other, you're going to be very confused. Just because the path split, think if you're walking along a path, just because there's two options doesn't mean the road suddenly goes downhill. Just because you took a right, the road splits, that doesn't mean that one end is down and one end is flat. It just means that the path splits. It means that you have choices now. The water has different paths it can flow, and it will drop on each of those paths, but it's going to drop the same amount. Notice that they drop the same amount. What phrase do we use for how much they drop? The potential difference is the same. The potential difference here, let's call this delta V1. The potential difference here, delta V2. They're the same. Why? Because they start at the same height, they end at the same height. Why do they start at the same height and they end at the same height? Because there's just a bunch of wires on each side. Wires don't change the voltage. They're just pathways. They're just roads. What changes the voltage? Capacitors, resistors, batteries, actual circuit elements. Okay. So the voltage doesn't change, but something else does. And it'll be kind of easier to show in another picture. But yeah, parallel is trickier to understand, but this picture I think does a good, I like this picture because it shows this height analogy of seeing that they both get the same height drop. One wheel could be bigger, wider or thinner. So that's what they tried to show here. It's really subtle, but this left wheel is thinner and the right wheel is wider. We don't care about how, when it comes to voltage, we don't care about how much room the water has. We just care how much it drops. And they both drop the same. Parallel is one of those notoriously tricky things to teach. And so my question to you is, which of the following is a parallel circuit? And I got some crazy diagrams I made. Let's actually, let's see. All right, pick all the ones that are in parallel. Remember, you're not looking at, clearly a lot of these, only one of these actually is physically parallel. You're not looking at whether they're physically parallel. You're looking at, do they start with the same voltage? Do they end with the same voltage? That's what you're looking at. Do they start with the same voltage? Do they end with the same voltage?
Because you get the same endpoint, and that's all you care about. I don't know.
It's something that is yeah, that means height and RF. Let's pick up first one. So we kind of look at that.
I think B would actually.
Remember, wires don't split. So that voltage is 5 volts. So we kind of draw it because it's going to be kind of tricky to.
Well, think about. Start from one.
Yeah. Oh yeah. Go for it. Oh yeah. Great. Go ahead.
And then what they have with so do 7.
Think about the direction that you can go.
That A, you can go to sometimes look at it and not.
So here's all fine. Everyone gets one bar. What's the voltage? So the definition of parallel that's another way of doing it. Yeah, just go through these pictures. And that color coding is the type of power. Or that exactly. All right, to give you all the technique while this is still open, I'm going to do the first one, and I'm going to show you this technique with color coding it because I think it makes it nice. So what we do is we say everywhere on this red line is 5 volts. This wire splitting doesn't change that. It's still 5 volts here. It's still 5 volts here. What changes the voltage? A capacitor, a resistor, a battery. So until I run into one of those, the voltage is the same everywhere on that wire. 5 volts, 5 volts, 5 volts everywhere. Then we do the same thing on this side. This is 0 volts. Everywhere on this blue line is 0 volts until I hit a capacitor, resistor thing. 0 volts, 0 volts, 0 volts, 0 volts. What's the definition of parallel? I start with the voltage, I end with the same voltage. This one on the left, what voltage does it start with? 5. What does it end with? Great, let's do the other one. What does this one start with? What does it end with? Oh my gosh, it's the same. They're in parallel. Do that for the rest. To check. That's how you can check the rest.
Wait, so the beginning of each.
Yeah, we're going to be
Yep.
No, so just into each.
That's on purpose to show you that you don't worry about what the picture looks like. You worry about the voltage. Like, that's the thing you focus, not the physical, whether or not they're actually parallel. You worry about how the voltage. They are all parallel. This is I purposely picked a bunch of crazy different looking ones to show you it's not about the physical where they're oriented. It's all about the voltage. If it's the exact same voltage, they're parallel to each other. Yep. Oh yeah, I think the curve is supposed to be positive. I just put that to show you that there's other ways to draw it, and I think I might have put that in. I'm not going to use that one, but that I guess is common name. When on the circuit builder I used online, it called that like US way of doing it, and it called the flat ones IEC, maybe international something. I don't know. We tend to always draw them like this. There's a chance that these ones might be like the wrong way. I have to double check. Honestly, don't. I never use this curve notation, but I guess it's a way that, like in the U.S., they might draw capacitors. I just put this here to show you this is a capacitor. Don't worry about what side the curve thing's on. Don't worry about that. I have to double check myself on this. All right, give y'all 10 more seconds at this point. All right, in 5, 4, 3, 2, 1. All right, so through the magic of color coding, this one's blue, all red on one side. This one's all blue on one side. Yep, that's in parallel because they both start with the same and they end with the same. This one starts with red. It all ends with blue. Oh, look, that one's also parallel. Oh, this one, they both start with red and they both end with blue. So those are also parallel. They're all parallel. The whole point of this exercise is to not get you the bad habit that everyone ends up in is that they're like, oh, they need to look like this. No. What I need to get you on the mindset of is parallel doesn't mean that they're physically parallel to each other. It means they start with the same voltage and they end with the same voltage. The definition of parallel is that the voltage drop is the same across them because of this. That's the really important thing here. Boom, 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 boom. I don't know if that worked. I don't even know that you picked all the answers. Hopefully so. Whatever. Great. So, remember the definition is such that they're the same. I'm going to pick the easy picture, but voltage being the same, voltage being the same. So what does this mean about the voltage across capacitors in parallel? I've said this like a bajillion times. The voltage is the same. Yeah. Okay. Why is this useful? So the voltage here equals 5. The voltage here equals 5. It's the same. We'll put the units because we're good. All right. In parallel, voltage is the same. To make it easier, we can combine them just like we did last time. And it's going to have the same voltage as each capacitor, but there's also something I'm going to show you all. So their charge can be different though. So this is what, the voltage will be the same, but the charge can be different. So maybe this one gets Q1 and this one gets Q2. They're going to get different charges. Why? Remember y'all C equals Q over V? So if I rearrange this, if they both get the same voltage, but they have different capacitances, they're going to get different charge. You can see that from the math. Same voltage, different capacitance means different charge. So that's the logic there. Now, the trick we're going to use to combine these, I purposely chose these ones because it's really easy to show something. If I turn these into one capacitor, it's basically like I just combine these plates together. That's kind of one way of thinking about it. So I'm turning this into one capacitor that looks like this. One big old capacitor, C, let's call it net. Let's start using that terminology. It still is going to have the same delta V, but it's going to have some total charge. If I literally took these two capacitors and connected them together, what's the relationship between Q1, Q2, and Q total? Q total equals Q1 plus Q2. Because it's as if I took these two capacitors and just like stuck them together. The charge in the total capacitor is the same as add the other two together. Because it's effectively like we just took them and stuck them together. All right, so this one, normally I'd have you all work through it, but I'll like work through it just so we can get out of here. Because I think I put enough in your brains. So this one, so Q total equals Q1 plus Q2. That's where we're going to start. Now we're going to do C equals Q over V. Same thing like we did before, but now we're going to solve for Q. So what does that equal? You all tell me. Q equals CV. Through the magic of putting that in here, C net times V equals C1 times, and I'm going to put these delta V's. Delta V, C1 times delta V plus C2 times delta V. Remember the definition of parallels. How do these voltage drops compare? They're all the same. Boom, gone, gone, gone. So in series, the capacitors just add together to give you a big capacitor. And visually, it's very easy to see why that's the case. You could just imagine literally sandwiching these things together and you made a bigger capacitor. That one's kind of easier to show visually.
So with series, it was delta V equals V1 plus V2, but
Yeah.
delta V equals V1 equals V2.
Yeah, so the difference, this one we did the charges add to get you the total charge. The last one, the voltage is added together to get you the... What stayed constant changed. In series, charge stayed constant. In parallel, voltage stays constant. And the consequence of that is how you add the capacitors changes. In parallel, you just add them up. It's easier. And we're going to eventually learn that resistors follow the opposite rules. Specifically, how you add them together. They still follow that the voltage is the same in parallel, but the addition rules for resistors will be opposite. That's like test 2 stuff, though. So that's it. Next class, we'll make sure this made sense, and we'll do this problem, and it's going to be great. And then we'll do resistors and currents, and we'll do a lab on capacitors. We're going to build our own capacitors. I was so excited about doing it today, but sad. Next time.
Did somebody ask you about curve.
Yes.
Faster.
Yeah, right. I'm so